Please subscribe to support the channel. How big is the universe? It is a question that instantly opens the door to wonder, because it doesn't just ask for a measurement, it challenges the very edges of human imagination. For as long as we've looked to the skies, this question has echoed in our minds. Philosophers pondered whether the cosmos was finite, enclosed within some great sphere, or infinite, stretching endlessly in every direction. Today, despite our technology, satellites, and telescopes peering into deep space, we still wrestle with the enormity of the universe. The power of this question lies in its simplicity. At first, it seems like something that should have an answer, like measuring a road, or the size of an ocean. But as soon as we try to define it, we realize that the universe operates on scales so vast that ordinary ways of thinking fall short. The very act of asking reminds us of how small we are, a species clinging to a pale blue, staring out into an abyss that may be infinite. And yet, that smallness doesn't feel like defeat. Instead, it feels like awe, like being part of something so grand that the mystery itself becomes a source of beauty. This question is timeless because it taps into both science and spirit. It ties us to the earliest humans who first tracked the stars and to the scientists who now chart galaxies billions of light years away. No matter how much we discover, the question lingers: is there an edge? Or does the universe go on forever? That deep, haunting curiosity is why we keep looking upward, why we keep building better telescopes, and why, no matter what, the mystery of the universe's size will always captivate us. When we start to talk about the size of the universe, the first thing we have to accept is that the normal yardsticks of our daily lives are utterly useless. The scales we're familiar with, meters, kilometers, maybe thousands of kilometers when we talk about continents or flights, collapse into insignificance the moment we step beyond Earth. To even begin this journey of understanding, we need to stretch our minds to think in distances that dwarf everything we experience. Let's take a modest step out from our planet. The Moon, our closest celestial neighbor, is about 384,000 kilometers away. That's so far that if you drove there at highway speed, it would take months of non-stop driving. Yet, on the cosmic scale, that distance is so small it's practically nothing. It's like the tiniest grain of sand compared to a mountain. Now look at Earth's orbit around the Sun. That distance is about 150 million kilometers, and astronomers have created a special unit just to describe it, the astronomical unit. We use this as a measuring stick for distances within our solar system. But again, when you step back further, even 150 million kilometers is still just a whisper compared to the vastness of space. The nearest star system to us, Alpha Centauri, sits over 4 light-years away. And here we run into the first clue about how far beyond everyday thought the universe really is. We need a whole new concept of measurement. Instead of kilometers, we use light-years, the distance light itself can travel in a year. Remember, light moves at the ultimate speed limit of 300,000 kilometers every single second. And yet, even at that breathtaking pace, it still takes over 4 years for light to travel from Alpha Centauri to Earth. So when we say the universe is vast, we don't just mean bigger than countries or planets. We're talking about scales so immense that they reshape how we think. The Milky Way galaxy, our cosmic home, is about 100,000 light-years across. That means if you could send a beam of light from one side of our galaxy to the other, it would take 100,000 years to make the trip. And here's the kicker: the Milky Way is just one galaxy among trillions scattered through the universe. Once you realize that, the question of scale becomes almost dizzying. You start to feel the same way people must have felt centuries ago when they first learned that Earth wasn't the center of the universe, but a tiny part of something bigger. Each leap in scale humbles us a little more. Our Earth, vast to us, is nothing compared to the Sun. The Sun, massive as it is nothing compared to the galaxy. And the galaxy, enormous and majestic, is just one dot in an endless cosmic web. To really understand the size of the universe, we have to practice letting go of everyday intuition. Numbers like billions and trillions stop meaning much when we use them casually, but here they represent real distances. A billion light-years isn't just a figure, it's the span across clusters of galaxies, each one filled with stars and planets. The human brain isn't wired to grasp this easily, but that's exactly why this topic is so powerful. It forces us to expand our imagination, to embrace scales that seem almost impossible. And this is just the beginning, because before we can measure the universe, we first need to ask, what exactly do we mean when we say the universe? Are we talking about everything that exists, or just what we can see? That's the next step in our journey, defining the universe itself. When we ask about the size of the universe, it is vital that we pause and agree on what we mean by the word universe. Because without that clarity, the conversation easily drifts into confusion. The universe, in the broadest and most accepted scientific sense, is everything, every speck of matter, every bit of energy, every particle of dust floating in intergalactic space, every blazing star and swirling galaxy, every field and force, and even the very fabric of space and time in which all of it exists. It is not just what we see when we look through a telescope. It is not just the stars, or the galaxies, or the cosmic background glow. It is literally all of reality as far as we know it, the container that holds everything. That means the universe is not just a place filled with things, it is also the stage itself. Time is part of the universe. Space is part of the universe. The laws of physics themselves, the way gravity works, the way light moves, the way particles interact, all of these are features of the universe. When we say the universe, we are talking about the totality of existence. If something exists, whether it is a star, a black hole, or even you listening right now, it is part of the universe. This makes the question, how big is the universe, even more profound, because we are essentially asking, how big is everything? How far does reality extend? Where, if anywhere, does it stop? And if it doesn't stop, if it goes on forever, then what does forever truly mean? It's worth noting that this definition also rules out the idea of outside the universe, at least in the traditional sense. If the universe is everything, then what could outside mean? There's no space beyond space, no time beyond time, at least not in a way that fits with our current understanding. That doesn't mean other realms or multiverse are impossible. In fact, some theories suggest that our universe might be one bubble among countless others. But when we say the universe, we are speaking specifically about the reality we inhabit, the one that includes all known dimensions of space and time. It also means the universe is not just about matter, the stuff we can touch or see. Matter is only a small fraction of the total cosmic inventory. The universe also includes energy in its many forms, radiation, light, heat, and especially the strange forces we barely understand, such as dark energy. And let's not forget dark matter, an invisible form of matter that does not emit or absorb light but reveals itself through its gravitational pull. These mysterious components remind us that even though we define the universe as everything, most of that everything is still largely unknown to us. We've only uncovered a fraction of the puzzle. In practical terms, when we try to measure the universe, we usually mean the observable portion of it, the part that light has had time to reach us from. But that's a limitation of our perspective, not of the universe itself. The universe as a whole might be infinitely larger than what we can ever see. It could be finite but unbounded, like the surface of a sphere in 3 dimensions. Or it could extend into structures and realms beyond what our physics can currently describe. Another important element of this definition is time. The universe includes the past, the present, and the future. When cosmologists talk about the universe, they're not just describing the stars that shine today, but also the birth of the cosmos 13.8 billion years ago in the Big Bang, and the possible futures billions or trillions of years from now. In that sense, the size of the universe is not only spatial, it is also temporal. The universe stretches across time just as much as it stretches across space. Every second that passes, every tick of the clock, adds to the story of the universe. This definition is awe-inspiring because it places us inside the greatest framework imaginable. You, me, the Earth, the solar system, our galaxy, all of it is woven into this cosmic whole. The universe is not something out there that we peer into. It is the very reality that holds us. When we talk about measuring its size, we're talking about trying to wrap our finite minds around the totality of existence. And that is why the question is so powerful, because it presses us against the limits of knowledge itself. Now that we've clarified what we mean by the universe, all of space, all of time, all of matter, all of energy, the next step is to recognize that our ability to measure it comes with restrictions. No matter how powerful our telescopes become, no matter how sophisticated our theories, there is a built-in boundary to what we can observe. That leads us directly into the concept of the observable universe, the part we can actually access through light and signals that have had time to reach us across the cosmic ocean. When we begin to speak about the observable universe, we are no longer discussing the entirety of reality but rather the slice of it that we, bound by the limits of physics, can actually access. The observable universe is not a separate entity from the universe itself. It is simply the region of the whole that has revealed itself to us because light and other signals have had enough time to travel across space and reach our instruments here on Earth. Imagine being in a vast dark plane, holding a lantern, and being able to see only as far as the glow of the lantern stretches. Beyond that glow, the plane continues, but you cannot perceive it. That is the relationship between the universe and the observable universe. The observable universe is dictated by one unyielding factor: the finite speed of light. Since nothing can travel faster than light, there is a maximum distance from which information can ever reach us. And because the universe has a finite age, about 13.8 billion years, that means we can only see objects whose light has had time to arrive here during that period. Everything else, no matter how real or how vast, lies beyond our cosmic horizon, forever hidden from us unless physics itself has some deeper secret that allows information to move faster than light. This idea transforms the way we think about the universe. We tend to imagine that when we look through a telescope, we're seeing the universe as it is, but that isn't quite true. What we're really seeing is the observable universe, a cosmic bubble centered on us with a radius defined by the travel of light through time. Importantly, this doesn't mean Earth holds some privileged position in the cosmos. Every observer, no matter where they are in the universe, has their own observable universe centered around them. A galaxy a billion light-years away has its own bubble, overlapping with ours but stretching into regions we'll never glimpse. The sheer size of the observable universe is mind-bending. Because of the way cosmic expansion works, the radius isn't simply 13.8 billion light-years. In reality, the farthest regions we can detect today are about 46 billion light-years away. That means the observable universe forms a sphere roughly 93 billion light-years in diameter, filled with galaxies, clusters, and filaments of matter. This is only the portion revealed to us. The true universe could be far larger, possibly infinite, extending into regions forever unreachable. When we talk about the observable universe, we're not talking about a physical wall or a barrier. It isn't like there's a dome with stars painted on it at the edge of space. Instead, it's a horizon, similar to the horizon you see standing at the edge of the ocean. The ocean doesn't stop at the horizon. It continues far beyond, but your eyes can't follow it. In the same way, the universe doesn't end where our observations stop. It keeps going, in ways we can only their eyes about. This distinction, between the observable and the total, keeps our perspective humble. It's easy to fall into the trap of thinking we've mapped or measured the whole of existence, but we've only scratched the surface. Everything we see through the most advanced telescopes, from the nearest star to the faintest, most ancient galaxy, is part of this observable region. Beyond it may lie an expanse of unimaginable proportions, teeming with galaxies we will never witness, light that will never reach us, and mysteries we cannot even begin to frame in human language. The observable universe also serves as a reminder that in cosmology, we are always looking into the past. The farther away an object is, the longer its light has taken to reach us. When we observe galaxies billions of light-years distant, we are not seeing them as they are today but as they were billions of years ago. In this sense, the observable universe is also a time machine. It allows us to trace the story of the cosmos back toward its beginning, all the way to the faint afterglow of the Big Bang itself. By understanding the observable universe, we gain perspective. Our cosmic vision is limited not by the scale of our instruments but by the very structure of reality. And this leads us naturally into the principle that underpins everything we can or cannot see: the speed of light, the universal speed limit, which defines the horizon of our knowledge. The foundation of our understanding of the observable universe rests on one of the most fundamental principles in physics: the speed of light. At nearly 300,000 kilometers per second, light is the fastest thing in existence. No matter how powerful a rocket we build, no matter how much energy we could one day harness, nothing with mass can ever outrun it. It is not just fast, it is the ultimate speed limit woven into the fabric of reality itself. This limit isn't an arbitrary restriction imposed by nature. It is a direct consequence of the way space and time are structured. Einstein's theory of relativity showed us that space and time are not separate entities, but parts of a single fabric called space-time. Within this framework, the speed of light is not simply a velocity. It's a boundary that defines how information, energy, and causality flow through the cosmos. If anything could move faster than light, the entire logical structure of cause and effect could collapse. Events might occur before their causes, and reality as we know it would unravel. In that sense, the speed of light is as much about preserving the coherence of the universe as it is about physics itself. Because of this limit, our vision of the cosmos is inherently restricted. When we look out into space, what we are really doing is gathering light that has been traveling across unimaginable stretches of time to reach us. A star 10 light-years away appears not as it is in this moment, but as it was 10 years ago. A galaxy a billion light-years away shows us a snapshot from a billion years in the past. We are not seeing the present universe, we are watching an ancient movie unfold, each photon of light carrying with it a story from some earlier time. This is why the observable universe is finite, even if the universe itself is infinite. Light simply hasn't had enough time to cross the full extent of reality and arrive here. Since the cosmos is 13.8 billion years old, we might assume that we can only see about 13.8 billion light-years out. But due to the ongoing expansion of space itself, the actual radius of the observable universe is closer to 46 billion light-years. Still, that limit exists only because light, bound by its maximum speed, hasn't been able to bring us news of what lies beyond. The speed of light is also a humbling reminder of just how small and slow we are in comparison. If we could somehow build a spacecraft capable of traveling at 99.9% the speed of light, it would still take over 4 years to reach Alpha Centauri, the nearest star system. To cross the Milky Way would require tens of thousands of years. To reach the edge of the observable universe would be hopeless. Tens of billions of years of travel, during which the universe itself would continue expanding, pulling distant galaxies even farther away. The light speed limit not only shapes what we can see but also what we can imagine. For instance, if a civilization exists in a galaxy 60 billion light-years away, its light will never reach us. Their reality is forever hidden from ours, as if sealed off by an invisible cosmic curtain. To them, we are equally unknowable. This means that the universe could be filled with wonders, galaxies, stars, civilizations, that are completely inaccessible, not because of any failure of technology but because of the fundamental structure of reality itself. Even here on Earth, the finite speed of light has strange consequences. When we look at the sun, we don't see it as it is now but as it was about 8 minutes ago, the time it takes for light to cross the 150 million kilometers between Earth and the sun. If the sun were to vanish suddenly, we wouldn't know for those 8 minutes. In that small delay is hidden the same principle that governs the entire observable universe. Light connects us to the cosmos, but always with a time lag, always with the reminder that what we see is history, not the present moment. Understanding this limit is crucial, because it explains why our universe has a horizon at all. Without the restriction of light speed, we might be able to see everything at once, perceive the entire cosmos as it truly is in this moment. But instead, we live in a universe where knowledge must wait for light to arrive, where vast distances equate to deep stretches of time. This intertwining of space, time, and light is what gives cosmology its strange beauty. To look outward is always to look backward. And as we reflect on this, the next natural question arises: how long has light actually had to travel? To answer that, we must consider the age of the universe itself, 13.8 billion years, because that number sets the ultimate boundary on how far light has been able to journey and how much of the cosmos we can ever observe. The age of the universe is one of the most remarkable numbers ever uncovered by science, and it is central to our understanding of its size. Through decades of observation, calculation, and refinement, cosmologists have converged on a figure. The universe is about 13.8 billion years old. That number doesn't come from guesswork, it emerges from careful study of cosmic expansion, the behavior of galaxies, the oldest starlight we can detect, and the faint afterglow of the Big Bang itself, the cosmic microwave background. This number, 13.8 billion years, is staggering, yet it is also precise in a way that reflects humanity's ability to measure something as vast as time itself. To put it in perspective, Earth is about 4.5 billion years old. That means the universe existed for nearly 9 billion years before our planet even formed. Dinosaurs disappeared 65 million years ago, which might seem like an eternity in human terms, but compared to the age of the universe, it is the blink of an eye. Human civilization has existed for only a few thousand years, a span so short that it barely registers on the cosmic calendar. If the history of the universe were compressed into a single year, all of recorded human history would take place in the last second of December 31st. The age of the universe is important because it sets a natural boundary for what we can see. Since light has a finite speed, it has had only 13.8 billion years to travel. That means, in principle, the farthest light we could observe should come from a distance of 13.8 billion light-years. This boundary is not arbitrary, it is the limit imposed by the finite age of everything around us. No signal from farther away could have had time to arrive, because the universe itself hasn't existed long enough for it to do so. But there's a twist that makes the situation more complex and fascinating. Space itself has been expanding ever since the Big Bang. As light traveled toward us across billions of years, the very fabric of space stretched, carrying distant galaxies even farther away. That means the galaxies that emitted the light we see today, 13.8 billion years after the beginning, are no longer 13.8 billion light-years distant. Instead, due to cosmic expansion, they are now about 46 billion light-years away. This is why the observable universe is so much larger than the naive calculation of age times the speed of light would suggest. The number 13.8 billion years also represents more than just a span of time. It represents the unfolding story of everything that exists. At the very beginning, the universe was a hot, dense plasma where matter and energy were almost indistinguishable. In the first fractions of a second, forces separated, particles formed, and the seeds of structure were sown. Within minutes, hydrogen and helium were forged in a process called Big Bang nucleosynthesis. Hundreds of millions of years later, the first stars ignited, casting light into the cosmic darkness. Galaxies slowly assembled, clustering together under the pull of gravity, weaving the vast cosmic web that stretches across the observable universe today. Knowing the age of the universe allows us to situate ourselves within this grand story. We live at a time when stars and galaxies are mature, when heavy elements like carbon and oxygen, the building blocks of life, have already been forged in generations of stellar furnaces. We exist in a universe old enough to have created planets and life, yet still young compared to the infinite future that might lie ahead. This perspective is humbling, because it tells us not only how far we can see but also when in the universe's life cycle we have appeared. It also challenges us to think about what lies beyond the observable. If the universe is 13.8 billion years old, and if light defines the cosmic horizon, then everything beyond that horizon is hidden from us, not because it doesn't exist, but because there hasn't been enough time for its light to reach us. There may be galaxies, clusters, or even entire structures of unimaginable size lying just beyond the edge of visibility, permanently veiled. The finite age of the universe is both a gift and a limitation. A gift because it gives us a way to measure and understand reality, and a limitation because it reminds us that our vision of the cosmos will always be incomplete. This number, 13.8 billion years, therefore functions as a cosmic clock, and it sets the stage for the next part of the story. If light has been traveling for nearly that entire span, what does it mean for the signals we now receive from the farthest galaxies? How does that journey of light across the great cosmic gulf shape our view of the universe? To answer that, we must turn our attention to the idea of light travel distance, the immense journeys photons have taken to bring us a picture of the ancient cosmos. When we look up at the night sky, it feels as if we are seeing the universe as it is right now. The stars sparkle, the galaxies shimmer faintly in telescopic images, and everything seems immediate, present. But in truth, we are never seeing the universe in the present. We are always looking into the past, because light takes time to travel. The farther away an object is, the older the image we are receiving. This is what makes the concept of light travel distance so extraordinary. Consider the Sun. It sits 150 million kilometers away, and light from it takes about 8 minutes to reach Earth. That means when you look at the Sun, you are not seeing it as it is in this instant. You are seeing it as it was 8 minutes ago. The same principle applies to the Moon, which is just over 1 second of light travel away. Everything you see in the sky has a time delay built in, a cosmic lag that ties distance to history. Now stretch that principle outward. The nearest star beyond our Sun, Proxima Centauri, is a little more than 4 light-years away. When you see its faint glow through a telescope, you are looking at light that began its journey 4 years ago, in a world where human lives have shifted and changed many times since that photon first left its star. Scale outward again. The Andromeda Galaxy, our nearest large galactic neighbor, is more than 2.5 million light-years away. The light that now enters your eyes left Andromeda when early humans on Earth had not yet learned to walk upright. Every time we look at Andromeda, we are seeing ancient history written across the sky. Now consider the farthest galaxies we have detected with the most powerful telescopes. Their light has been traveling to us for nearly 13.8 billion years, the vast majority of the age of the universe itself. The photons that arrive in our detectors today began their journey when the universe was in its infancy, when galaxies were just starting to form, when stars were first being born, when the cosmos was only a fraction of its current size. Each photon carries within it the memory of that early universe, stretched and weakened by the expansion of space, but still delivering its message across eons. This is what makes astronomy unlike any other science. It is inherently an act of time travel. To study the cosmos is to peer backward through history, to see how galaxies evolved, how stars were born and died, how the universe itself matured. Our telescopes are not just instruments of sight, they are machines that allow us to reconstruct the story of everything that has ever existed. Light travel distance transforms space into a living archive. But the story grows even stranger. Because the universe has expanded during the journey of that light, the galaxies we see at those immense distances are not still located where we perceive them to be. By the time their light has reached us, they have been carried away by cosmic expansion, receding far beyond the position they once held. This means the light from the most distant galaxies we observe began its voyage almost 13.8 billion years ago. But those galaxies are now about 46 billion light-years away. Light travel distance and actual present-day distance are not the same thing, and that difference is key to understanding the true scale of the cosmos. The concept of light travel distance also redefines our sense of now. When you look at the farthest observable galaxies, you are not seeing them as they are today but as they were in their infancy. To see them as they are now, you would have to wait billions of years for their current light to arrive. By then, both they and we may be completely transformed, perhaps even unrecognizable compared to what we know today. This realization is profoundly humbling. It tells us that even though we measure the universe with incredible precision, what we are really seeing is a story frozen in time, a series of still frames captured at different points across the cosmic timeline. Our picture of the universe is not a snapshot of the present, but a tapestry woven from billions of years of light travel. And yet, this same principle is also what gives us the power to understand cosmic origins. Because light takes so long to travel, we can look deeper and deeper into space and effectively watch the universe rewind itself. We can trace galaxies back to their younger forms, witness the afterglow of the Big Bang, and glimpse what the cosmos was like when it was less than 500,000 years old. Light is both messenger and historian, carrying the story of creation across unimaginable gulfs of time and distance. But there is one more twist. Light doesn't just travel, it stretches. As it journeys across expanding space, its wavelength grows longer, shifting toward the red end of the spectrum. This effect, called redshift, is one of the most important clues to understanding not only how light travels, but also how the universe itself evolves. The universe is not static. One of the most revolutionary discoveries in modern astronomy is that space itself is expanding, a concept that reshapes how we think about distances, time, and the very structure of reality. When we say that galaxies are moving away from us, it is not because they are traveling through a pre-existing stage, like cars driving down a road. Instead, it is the fabric of space itself that is stretching, carrying galaxies along like raisins embedded in a rising loaf of cosmic dough. This expansion is not limited to galaxies. It affects the very space between them, the voids, and even the light traveling across billions of light-years. This realization came from careful observation of distant galaxies. In the 1920s, Edwin Hubble discovered that nearly all galaxies outside our local group are moving away from us, and the farther they are, the faster they recede. This relationship, known today as Hubble's law, was evidence that the universe itself is growing. It was not just that galaxies were moving, but that the entire cosmic grid is stretching, increasing the distances between all points over time. This expansion occurs everywhere, in every direction, with no center or edge. Every observer in the universe, no matter their location, sees the same pattern. Distant galaxies moving away, carried by the swelling of space itself. The expansion of space has profound consequences for light traveling across the cosmos. As photons journey from distant galaxies toward Earth, the stretching of space elongates their wavelength. This process, known as cosmological redshift, shifts light toward the red end of the spectrum. A galaxy that originally emitted blue or ultraviolet light billions of years ago might now appear deep red or even infrared because the universe has stretched the light on its long voyage. This stretching is not due to the galaxies moving in the conventional sense. It is the expansion of space itself that causes the effect. In other words, the universe is not just a stage upon which light moves, it is a dynamic participant in the journey of light across cosmic distances. Cosmic expansion also complicates our understanding of distance. In everyday life, when we measure how far away something is, the measurement is straightforward. But in an expanding universe, distances are dynamic. The farther away a galaxy is, the faster it appears to recede because there is more space expanding between us. Light emitted from a galaxy billions of years ago traveled through a universe that was much smaller than it is today. By the time that light reaches us, the galaxy has moved much farther away due to expansion. This is why the radius of the observable universe is not simply 13.8 billion light-years, despite the age of the universe. The expansion has carried those galaxies to present-day distances of approximately 46 billion light-years. This expansion is accelerating, too, due to a mysterious phenomenon called dark energy. While gravity acts to slow the separation of galaxies over time, dark energy exerts a repulsive effect, pushing space itself apart at an ever-increasing rate. The implications are staggering. Distant galaxies will continue to recede faster and faster, and eventually, some may move beyond our observable horizon entirely, leaving us unable to see them no matter how advanced our instruments become. Space expansion is not just a passive backdrop, it actively shapes the limits of human observation and the structure of the cosmos. The stretching of light also allows us to see further back in time than we otherwise could. Because the universe was smaller when the light was emitted, the photons we receive from the earliest galaxies have traveled a shorter initial distance, even though the space they traversed has expanded enormously. This interplay between cosmic expansion and light travel is why we can observe galaxies that emitted their light when the universe was just a few 100 million years old, even though those galaxies are now tens of billions of light-years away. In effect, cosmic expansion makes the universe a dynamic, living system, where distances are not fixed, light is stretched, and what we see is continuously transformed by the growth of space itself. It turns the simple act of observation into a complex interplay between space, time, and history. Every photon of light carries the story of not just the galaxy it originated from, but also of the expanding medium through which it traveled, a medium that itself is changing the scale of the cosmos while we watch. This concept leads directly to one of the most important observational tools in cosmology, redshift. The stretching of light provides a map of the universe's expansion history, allowing astronomers to measure how fast galaxies are receding and how the universe has grown over billions of years. By decoding these subtle shifts in wavelength, we can reconstruct the expansion rate, understand the influence of dark energy, and trace the evolution of cosmic structure from the early universe to today. In short, cosmic expansion transforms our understanding of the universe from a static backdrop into an evolving, dynamic expanse, with light itself serving as both witness and messenger. Every distant galaxy we see is part of this grand story, carried across billions of years by a universe that is constantly growing. And it is this expansion, this stretching of space and time, that leads us naturally to the phenomenon of redshift, a subtle yet powerful signature of the universe's ongoing evolution. One of the most fascinating consequences of cosmic expansion is redshift, the stretching of light to longer wavelengths as it travels across the expanding universe. When we observe distant galaxies, we notice that the light they emit is shifted toward the red end of the electromagnetic spectrum. This is not just a visual curiosity. It is one of the most powerful tools astronomers have for understanding the scale, age, and structure of the universe. Redshift acts as a cosmic fingerprint, revealing the dynamic nature of space and providing a window into the history of the cosmos. To understand redshift, imagine light as a series of waves, each with a specific wavelength. When a galaxy emits light, that light begins its journey through space with a particular wavelength, corresponding to a color in the spectrum. As the universe expands, the fabric of space stretches, and with it, the wavelength of the light traveling through it. The longer the light travels and the more the universe expands during its journey, the more the wavelength stretches. By the time this light reaches Earth, the originally emitted wavelengths have shifted to the redder, longer end of the spectrum. This stretching is why the phenomenon is called redshift. Redshift is not caused by the motion of galaxies through space in the conventional sense, as one might think of a car moving down a road. Instead, it is the expansion of space itself that stretches the light. Every photon traveling across billions of light-years has its wavelength elongated along with the expansion of the universe. The farther away a galaxy is, the more space has stretched during its light's journey, and the greater the redshift. This is why distant galaxies often appear redder than we might expect based on the type of stars they contain. They are not intrinsically red, but their light has been elongated by the expanding cosmos. The measurement of redshift allows astronomers to quantify the speed at which galaxies are receding from us. The higher the redshift, the faster a galaxy is moving away, and typically, the farther it is from Earth. This relationship underpins Hubble's law, which connects distance and velocity and provides the first quantitative evidence for cosmic expansion. Redshift is therefore both a record of motion and a measure of distance, turning light into a cosmic yardstick that spans billions of light-years. Redshift also opens a window into the early universe. The most distant galaxies we observe have the highest redshifts because their light has been traveling for almost the entire history of the cosmos. By analyzing the redshift of these ancient photons, we can reconstruct the conditions of the universe when it was only a fraction of its current age. The light from the earliest galaxies carries imprints of their composition, temperature, and formation processes, allowing us to study cosmic evolution across billions of years. Moreover, redshift is critical for understanding the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB was emitted when the universe was only about 380,000 years old, in a period known as recombination. At that time, the light was much hotter and peaked in the visible or infrared range. Over billions of years, as the universe expanded, that light was stretched into the microwave range. Today, we detect it as a uniform glow at just 2.7 Kelvin, an extraordinarily low temperature. Without redshift, we would have no way of connecting this faint radiation to its origins in the infant universe. Redshift also has philosophical implications. It demonstrates that the universe is not static, frozen in time, but evolving, stretching, and growing. The galaxies we observe today were once much closer together, and their light tells the story of their migration across cosmic time. By observing redshift, we are not just measuring distances, we are witnessing history, reading a record of the universe's expansion written into every photon. Another fascinating aspect of redshift is that it challenges our intuitive sense of speed. Some of the most distant galaxies we observe have such high redshifts that they are receding faster than the speed of light relative to us, not because they are moving through space that fast, but because the space between us and them is expanding so rapidly. This is allowed by the laws of physics because relativity restricts motion through space, not the expansion of space itself. It is a counterintuitive reality that highlights the strange, almost surreal nature of the cosmos. Redshift, therefore, is much more than a measurement of color change. It is a key to unlocking the universe's size, the rate of expansion, the age of cosmic structures, and the dynamics of dark energy. It allows us to place galaxies on the timeline of the universe, understanding how they formed, evolved, and continue to drift apart in an expanding cosmic web. By carefully measuring redshift across many galaxies, astronomers can create three-dimensional maps of the universe, revealing the large-scale structure of clusters, filaments, and voids that stretch across billions of light-years. Ultimately, redshift reminds us that every photon reaching Earth carries with it a journey not only through space but through time, encoded with the expansion of the universe itself. It is a testament to the dynamic, ever-growing nature of reality, a signal of movement that is baked into the cosmos at its most fundamental level. Without redshift, our understanding of the universe's expansion, the observable horizon, and the very distances of galaxies would be incomplete. With it, we can quantify the vastness of space and glimpse the staggering scale that lies beyond. Redshift leads directly into an even more profound realization. Because space itself expands, the farthest observable galaxies are now much farther away than the 13.8 billion years their light has traveled. This stretching of light and space transforms our perspective of distance and brings us to the concept of the observable universe's true size in today's terms. One of the most mind-bending consequences of cosmic expansion is that the farthest galaxies we can observe are now much farther away than the simple calculation of the universe's age multiplied by the speed of light would suggest. If we only considered that light has been traveling for 13.8 billion years, we might assume that the farthest visible galaxies lie about 13.8 billion light-years from Earth. Yet the reality is far more astonishing. The expansion of space has carried those galaxies much farther away, and today they are approximately 46 billion light-years distant. This discrepancy arises because space itself is not static. As we discussed in the previous segment on cosmic expansion, galaxies are not merely moving through space. The fabric of space is stretching, dragging galaxies along with it. Imagine drawing a line on a rubber band and stretching it. The points on the line move apart, not because they themselves are moving, but because the surface holding them is expanding. In the same way, the universe stretches the distance between Earth and the most distant galaxies even as the light from those galaxies is making its way toward us. It's crucial to grasp what this means for our perception of distance. The light that left a distant galaxy billions of years ago traveled through a smaller universe, closer together in the early cosmos. Over time, however, the space between us and that galaxy expanded, lengthening the effective distance far beyond the 13.8 billion years that the light was in transit. This is why astronomers distinguish between look-back time, how long light has been traveling, and moving distance, which measures how far away an object is in today's universe. The most distant galaxies we can observe have a look-back time of nearly 13.8 billion years, but their current moving distance is roughly 46 billion light-years. This fact profoundly changes the way we understand the universe. The cosmic horizon, the boundary of the observable universe, is not merely a function of how far light can travel, but also a consequence of space itself stretching. It is as if we are in a boat on a river that is flowing and widening at the same time. Even if we row continuously toward a distant shore, the expansion of the river can carry the shore farther away faster than our rowing. Similarly, even as photons speed toward us at light speed, the expansion of space ensures that the original sources of that light are now far beyond where they were when the light began its journey. The scale of this distance is almost incomprehensible. 46 billion light-years is more than 3 times the product of the universe's age and the speed of light, illustrating just how different cosmic distances are from anything we experience on Earth. If we attempt to compare this to human scales, it's as if the journey is not measured in kilometers or miles, but in the very flow of space-time itself. Every galaxy, every cluster, every filament of the cosmic web has been carried along by this expansion, increasing the scale of the observable universe far beyond what might seem intuitively possible. Moreover, this distance underscores the dynamic nature of reality. Light arriving today from the edge of the observable universe is a message from a universe in its infancy, when structures were just beginning to coalesce from the primordial soup of matter and radiation. Meanwhile, those same galaxies are now billions of years older and vastly farther away. The universe is not a static snapshot. It is a living, growing entity, and the farther we look, the deeper we peer into both space and time simultaneously. This also sets up a fascinating paradox. In principle, there are galaxies whose light will never reach us. As expansion accelerates due to dark energy, some galaxies are receding so rapidly that even photons traveling at the universal speed limit will never close the gap. They lie forever beyond our observable horizon. In essence, we are limited not by the extent of the universe itself, which may be infinite, but by the interplay of light travel time and the stretching of space. This gives our observable universe a boundary defined not by a physical wall but by the history of cosmic expansion. The realization that the farthest observable galaxies are now about 46 billion light-years away also helps us quantify the observable radius of the universe. This radius, centered on Earth, or any point in space, for that matter, marks the edge of everything we can currently see. Beyond this radius lies the unobservable universe, regions that may be similar, larger, or infinitely different from our own, but which remain forever hidden by the finite speed of light and the ongoing expansion of space. This brings a profound sense of scale and humility. The universe is far larger than even the seemingly impossible number of 13.8 billion light-years would suggest. The expansion of space has amplified the distances, revealing a cosmos that is not only ancient but also staggeringly vast. It is an ever-growing realm, stretching the boundaries of what we can perceive and continuously redefining our cosmic horizon. Understanding these distances also prepares us to grasp the overall dimensions of the observable universe, including its diameter and the way astronomers think about its vast spherical extent. It sets the stage for appreciating not just the radius but the incredible span of 93 billion light-years across, encompassing all that we can see and measure from our vantage point in space. The radius of the observable universe is one of the most astonishing numbers in all of science, about 46 billion light-years. This distance represents the farthest we can see from our vantage point on Earth, limited by the combination of the finite age of the universe, the speed of light, and the ongoing expansion of space. It defines a spherical volume centered around us, encompassing everything whose light has had time to reach our telescopes since the beginning of the cosmos. While the number itself is almost impossible to fully grasp, understanding what it represents is essential for appreciating the enormity of the universe. It is important to note that this radius is not simply 13.8 billion light-years, the age of the universe in years multiplied by the speed of light. That would be a naive estimate, ignoring the fact that space itself has been stretching over the entire history of the cosmos. The galaxies that emitted the first photons we now detect as coming from the edge of the observable universe were much closer when the light left them, but as that light traveled toward us, the intervening space expanded, increasing the distance between us and the source. By the time the photons arrived, the galaxies were already tens of billions of light-years farther away. This is why the observable radius is approximately 46 billion light-years, more than 3 times the simple light travel calculation. This radius defines a cosmic horizon, the ultimate boundary of human vision. Beyond this, light has not had time to reach us, and therefore we cannot directly observe any objects that exist there. It is essential to understand that this horizon is not a physical boundary or an edge of the universe. There is no wall, no curtain, no edge in the traditional sense. Instead, the horizon represents a limit in our knowledge, a sphere within which all observable matter, galaxies, clusters, and cosmic structures reside. Every point in the universe has its own observable radius, meaning that other galaxies, if they had observers looking outward, would see a similar sphere of about 46 billion light-years around themselves. Within this radius, the observable universe contains an estimated 2 trillion galaxies, each filled with billions of stars and countless planetary systems. It encompasses galaxy clusters, superclusters, cosmic filaments, and vast voids stretching across billions of light-years. The cosmic web is revealed in remarkable detail through observations of light, redshift, and gravitational effects, painting a picture of a universe that is both structured and immense. The scale is so vast that the numbers involved defy human intuition. Even describing the observable universe as a sphere 46 billion light-years in radius is almost an exercise in futility, because the sheer magnitude is beyond everyday experience. The 46 billion light-year radius also underlines the dynamic nature of the cosmos. Objects near the edge of this observable sphere are not in the same location now as when their light began its journey. Over billions of years, space has expanded, carrying these galaxies outward at speeds that, for the most distant ones, exceed the speed of light relative to us, not violating relativity, because this motion is due to the expansion of space itself, not motion through space. This concept transforms our understanding of distance. We must think not only in terms of where things are now, but also in terms of where they were when the light we observe left them, and how much space has expanded in the meantime. The observable radius is intimately connected with the idea of look-back time. Light traveling from the edge of this sphere has been on its journey for almost the entire history of the universe, nearly 13.8 billion years. Observing these distant regions allows us to peer back in time, seeing galaxies as they existed in the early universe, providing a unique glimpse into cosmic evolution, galaxy formation, and the processes that shape the cosmos over billions of years. In essence, the radius of the observable universe defines the boundary of our temporal as well as spatial vision. Beyond this 46 billion light-year radius lies the unobservable universe, regions of space from which light will never reach us, at least not in the current age of the cosmos. These regions may contain galaxies, stars, or structures similar to those we can observe, but they remain hidden behind the limit imposed by light travel and cosmic expansion. The observable radius is thus a horizon, a window into the universe, defining the limits of our direct knowledge while hinting at the even greater vastness that lies beyond. Understanding the observable radius also provides the foundation for appreciating the universe's diameter, which is simply twice the radius. The diameter of the observable universe is therefore about 93 billion light-years, a staggering span that encompasses the entirety of the cosmic structures accessible to human observation. While the numbers themselves are difficult to visualize, they convey the immensity of what we can see, the richness of the cosmos within our reach, and the incredible scale of the environment in which our galaxy, and indeed our entire planet, exists. If the radius of the observable universe is about 46 billion light-years, then the diameter, measuring from one edge of the observable sphere to the opposite edge, is roughly 93 billion light-years. This is a mind-boggling distance, almost impossible to truly comprehend, yet it is a critical concept for understanding the scale of the cosmos. While we often think of distances in kilometers or miles in our daily lives, the observable universe operates on scales so immense that light-years and billions of light-years become the natural language for measuring reality. A diameter of 93 billion light-years emphasizes just how large the portion of the universe accessible to us truly is. Imagine a sphere with Earth at its center. Everything we can observe, from nearby stars to the most distant galaxies, lies within this vast cosmic bubble. Every point in this bubble represents a galaxy, a cluster of galaxies, or cosmic structures like filaments and voids. Each of these points is itself enormous. Our Milky Way galaxy alone is about 100,000 light-years across, and there are estimated to be over 2 trillion galaxies within this diameter. The scale of the universe is, quite literally, staggering. It is crucial to note that this diameter does not imply an edge in any conventional sense. The observable universe is defined by the distance light has traveled to reach us, not by a physical boundary. Beyond the 46 billion light-year radius from our location, there may be infinitely more galaxies, stars, and cosmic structures, but their light has not yet had time to arrive. The 93 billion light-year diameter is therefore a measure of our observational limit, not the size of the universe as a whole. This distinction underscores one of the profound truths of cosmology. We can measure what is observable, but the totality of existence may extend far beyond our view. Understanding the observable diameter also provides perspective on the age and evolution of the universe. Light from the most distant regions began its journey nearly 13.8 billion years ago, shortly after the universe formed. As this light traveled across space, the expansion of the universe stretched the distances involved, meaning that these ancient galaxies are now vastly farther away than when the light first departed. The 93 billion light-year diameter, therefore, is not static. It represents the current scale of the observable universe, accounting for billions of years of cosmic expansion. The enormity of this diameter also allows us to grasp the size of structures within the universe. Galaxy clusters, superclusters, and immense cosmic filaments stretch across millions or billions of light-years, all contained within the 93 billion light-year sphere. Large voids, regions of relatively empty space, span tens of millions of light-years. When combined, these elements form the cosmic web, a structure that, despite its complexity and scale, fits entirely within the observable universe's diameter. It is both humbling and awe-inspiring to realize that everything we have ever observed, mapped, or studied is contained within this single, incomprehensibly vast sphere. Even more astonishing is the human perspective on this scale. Earth, our planet, is just a tiny speck within the Milky Way, which itself is a single galaxy among trillions within the observable universe. The 93 billion light-year diameter is so vast that trying to imagine it is nearly impossible. Numbers that large are abstract and almost meaningless in our everyday experience. Yet they convey a truth about the universe. It is immense, structured, and filled with an unimaginable variety of cosmic phenomena. This diameter also reinforces the concept of cosmic horizons. Every observer in the universe has their own observable sphere with a similar diameter, centered on their location. In other words, every galaxy, every star system, and potentially every civilization would see its own 93 billion light-year sphere of observability, with overlapping regions but independent boundaries. There is no unique center of the observable universe. Earth simply happens to be at the center of our own observational bubble. Finally, recognizing the observable diameter prepares us to consider what lies beyond it. While we can measure a 93 billion light-year span, there is no guarantee that this sphere encompasses all that exists. The unobservable universe may extend far beyond this limit, potentially infinitely. This distinction between the observable and the total universe is central to modern cosmology, highlighting both the achievements and the limitations of our observational tools. The observable diameter of about 93 billion light-years thus encapsulates everything we can directly study and see. It frames the limits of human knowledge, contains the full history of light reaching us, and offers a window into the earliest epochs of cosmic history. Yet it is only a portion of the universe, a boundary of perception rather than a physical wall. Beyond it may lie regions as rich, complex, and unknowable as the observable cosmos, forever hidden from our view. While the observable universe is immense, stretching 93 billion light-years in diameter, it is crucial to remember that this is only the portion of the universe we can see. The term observable itself signals a limitation. It defines the boundary of what is accessible to us through light, radiation, or any other signals that have had enough time to reach Earth since the Big Bang. Beyond this limit lies the unobservable universe, a vast, likely far more extensive region that we may never directly witness. In other words, what we see is just a fraction of the total cosmos. The unobservable universe exists because of the fundamental constraints imposed by light travel and cosmic expansion. Light from regions beyond our cosmic horizon simply hasn't had time to reach us. Moreover, due to the accelerated expansion driven by dark energy, some regions of the universe are moving away from us faster than the speed of light relative to our position. This doesn't violate Einstein's theory of relativity, because that law restricts motion through space, not the expansion of space itself. Consequently, certain parts of the cosmos are, in principle, forever unreachable. No signal emitted from these regions will ever intersect with our observable sphere. This unobservable portion may be unimaginably large. Cosmologists speculate that the universe could extend hundreds, thousands, or even infinitely more light-years beyond what we can see. It might contain galaxies, clusters, superclusters, and cosmic structures just as complex, or more so, than those within the observable universe. Entire realms of matter, energy, and potentially even exotic forms of dark matter or other phenomena might exist beyond our observational limits. These regions remain hidden not because they are rare or unusual, but because the combination of light's finite speed and cosmic expansion has placed them forever beyond our reach. The concept of the unobservable universe challenges our intuition and even our philosophical understanding of space. Unlike the observable universe, which is framed by a horizon centered on Earth, the unobservable universe is not bound by any specific location. It is simply everything beyond our current horizon. Other observers, located in distant galaxies, would have their own observable universe, which would overlap with ours but also include regions entirely inaccessible to us. In this way, the universe is a mosaic of overlapping observational bubbles, each centered on a different vantage point, hinting at a vast continuity that stretches far beyond any individual perspective. Even more intriguing is that the unobservable universe may contain structures and features fundamentally different from those we know. While the observable universe exhibits remarkable uniformity on the largest scales, galaxies forming filaments, clusters, and vast voids, the unobservable universe could reveal surprises we cannot even imagine. It could host regions with different physical conditions, perhaps even variations in fundamental constants or novel forms of matter. In cosmological theories such as eternal inflation, our observable universe may be just one bubble among countless others, each with its own physics and properties, forming a vast multiverse. The existence of an unobservable universe also forces humility in our scientific conclusions. No matter how advanced our telescopes, instruments, or theoretical models become, there will always be a region beyond our reach. We can infer the existence of these regions through indirect evidence and theoretical extrapolation, but we cannot directly measure or experience them. The observable universe, as vast and detailed as it is only a window into a far greater reality, a reality that may extend infinitely in space and time. Moreover, the unobservable universe highlights the distinction between reality and perception. Our entire cosmological map, based on billions of years of light travel, only represents what is knowable to us from our location in space and time. Beyond our observational horizon, the universe may continue in every direction without end. It reminds us that the universe is not limited by our capacity to see it. Reality itself is far larger than what we can comprehend or measure. Understanding the unobservable universe also enriches our perspective on human significance. The galaxies, stars, and clusters we study are only a tiny fraction of what exists. Beyond our observable horizon lies an expanse so immense that even trillions of additional galaxies would be invisible to us. This realization emphasizes the humility required when contemplating our place in the cosmos. While we can explore, measure, and theorize, the full extent of existence likely remains forever beyond our grasp. The unobservable universe is a testament to both the vastness of reality and the limits of observation. It challenges us to think beyond what we can see, to imagine realms that may never reveal themselves directly, and to appreciate that the cosmic story is far larger than the slice accessible to our instruments. While we have mapped an extraordinary portion of the universe, the hidden expanse beyond the 46 billion light-year radius continues silently, a realm of infinite possibility and mystery. One of the most profound questions in cosmology is whether the universe is finite or infinite. While the observable universe has a defined radius of about 46 billion light-years, what lies beyond may not simply be more of the same, it might extend endlessly. The concept of an infinite universe is as mind-expanding as it is difficult to truly comprehend, and it carries profound implications for science, philosophy, and our understanding of reality itself. When cosmologists speak of a possibly infinite universe, they are referring to the idea that there may be no ultimate boundary to space. Unlike the observable universe, which is limited by light travel time and cosmic expansion, an infinite universe would extend forever in all directions. Every point in space would be surrounded by more space, stretching outward without limit. In this framework, the observable universe is just a tiny bubble in an incomprehensibly vast, or even infinite, cosmic expanse. Our measurements and observations would never capture the whole picture because there would always be more beyond the horizon. The possibility of an infinite universe arises naturally from several lines of evidence. Observations of the cosmic microwave background, CMB, show that the universe is remarkably uniform on large scales, with very little curvature. This suggests that space is flat, at least locally, and in a flat, uncurved universe, there is no natural endpoint to the spatial dimensions. While this does not definitively prove infinity, it is consistent with a cosmos that continues indefinitely. The implication is that what we see is a tiny fraction of a much larger, perhaps unbounded, reality. An infinite universe also carries mind-boggling consequences. In such a cosmos, all possible arrangements of matter could exist somewhere. There could be galaxies like our Milky Way, planets like Earth, and even regions nearly identical to our own, billions or trillions of light-years away. The sheer scale of possibility is beyond comprehension. Infinity transforms our notions of uniqueness and rarity. What we consider extraordinary or improbable may, somewhere in the infinite expanse, occur countless times. Yet infinity in physics is more than a philosophical idea. It is also a mathematical concept that fits naturally into modern cosmological theories. Many inflationary models suggest that the universe underwent a period of rapid expansion shortly after the Big Bang. This inflation could have stretched space to such an extent that it effectively becomes infinite, or at least so large that any curvature is imperceptible within the observable patch. In these models, the observable universe is a minuscule portion of an enormous, or boundless, cosmic tapestry. Considering an infinite universe forces us to rethink fundamental questions about existence. What does it mean to be here when space stretches endlessly? How do we define distance, location, or uniqueness in a universe that may have no edge? It also raises fascinating questions about repetition, probability, and the potential for regions that mirror our own galaxy, solar system, or even civilization. While we may never directly observe these regions, their hypothetical existence challenges our assumptions about space, matter, and the nature of reality. The concept of an infinite universe also affects cosmological measurement. While we can map the observable universe with increasing precision, infinity means that no matter how detailed our surveys, there will always be more beyond the horizon. Any measurement of size is inherently limited, a boundary defined not by the universe itself but by the finite speed of light and the universe's finite age. Infinity, by its nature, cannot be fully encompassed, yet it remains a consistent possibility within the framework of cosmology. It is worth noting that infinity does not imply chaos or randomness. Even if the universe is unbounded, it can still follow well-defined laws of physics. Galaxies can form clusters, stars can ignite, and cosmic structures can emerge in predictable ways, all within a potentially infinite canvas. Infinity does not preclude order. It merely expands the stage upon which cosmic evolution plays out. The idea of a possibly infinite universe also carries philosophical weight. It forces humanity to confront its relative smallness in the grand scheme of existence. Our planet, our galaxy, even our observable bubble may be infinitesimal within the totality of the cosmos. Yet this realization is not depressing, it is liberating. It highlights the extraordinary complexity and richness of reality, encouraging both curiosity and humility. The universe, whether finite or infinite, remains a realm of mystery and wonder, inviting exploration and reflection. Ultimately, the possibility that the universe is infinite extends the story of the cosmos beyond what we can see or measure. The observable universe, vast though it is, may be just a tiny glimpse into an unending expanse. Infinity challenges our imagination, tests the limits of human understanding, and inspires awe. Whether the universe is truly infinite or simply unimaginably large, the principle reminds us that reality far exceeds the limits of observation, and that the cosmos may be vaster than anything our minds can fully comprehend. The concept of the cosmic horizon is central to understanding the limits of what we can see in the universe. When we speak of the edge of the observable universe, it is crucial to realize that this is not a physical boundary, but rather a horizon defined by the finite speed of light and the age of the universe. In other words, the cosmic horizon marks the limit of what light has had time to reach us, not an actual edge where the universe stops. It is like standing on a beach and seeing the distant ocean stretch to the horizon. The water does not end there. The horizon simply marks the limit of what our eyes can perceive. The cosmic horizon is determined by how far light has traveled since the Big Bang. The universe is about 13.8 billion years old, so photons that have been traveling the longest define the edge of our observable sphere. However, because the universe has expanded while that light was in transit, the comoving distance to the edge of the observable universe today is about 46 billion light-years. The horizon is therefore not a static concept. It is dynamic, shaped by both the finite age of the universe and the ongoing expansion of space. Importantly, the horizon is not a barrier. It is not a wall that blocks us from seeing further, nor does it indicate that the universe ends there. Beyond the horizon, the universe continues, possibly indefinitely. We simply cannot access information from these regions because their light has not had enough time to reach us. Future generations of astronomers may see slightly farther as light from more distant regions arrives, but there will always be regions that remain forever beyond any observational reach due to the accelerating expansion driven by dark energy. The cosmic horizon also serves as a temporal boundary. Light reaching us from the farthest galaxies left those galaxies when the universe was much younger. Observing these distant regions is therefore equivalent to looking back in time, allowing us to see the early universe in its formative stages. The horizon is not merely a spatial limit, it is a record of cosmic history, the furthest moment in time we can observe from our location. The horizon concept highlights the relativity of perspective in cosmology. Every observer, no matter where they are in the universe, has their own cosmic horizon. An alien civilization billions of light-years away would see a different patch of the universe, with its own observable boundary. There is no universal center of the observable universe. Earth's position is central only to our observational sphere. In this sense, the horizon is a local concept, tied to the position of the observer rather than a global feature of the cosmos. The analogy of looking at a horizon helps to visualize this. When standing on a plain or a beach, the horizon appears to be an edge, yet the landscape extends far beyond it. Similarly, the cosmic horizon appears as a boundary in our observations, but the universe itself continues beyond, potentially without end. Every photon we detect from near the horizon has traveled across immense stretches of space and billions of years of time, carrying information from regions that, though currently at the edge of our sight, are not the edge of existence. The cosmic horizon is also intimately linked with the concept of redshift and the stretching of light. As photons from distant galaxies traverse the expanding universe, their wavelengths are elongated, shifting toward the red end of the spectrum. The light arriving from the most distant observable galaxies is heavily redshifted, indicating both the distance it has traveled and the expansion of space itself. The horizon marks the outermost limit from which such redshifted light has reached us, providing a natural boundary to observation while emphasizing that the universe extends beyond what we can measure. In essence, the cosmic horizon reminds us of both the power and the limitation of human observation. It defines the sphere of the observable universe, the region we can study in detail, map, and understand. Yet it simultaneously hints at the vast unknown beyond, the unobservable cosmos that remains forever hidden from direct view. It is a horizon in knowledge as much as it is in space, delineating the boundary between what is accessible and what is inaccessible, between what we can see and what lies beyond human perception. Understanding the cosmic horizon is critical for interpreting the observable universe correctly. It is not an edge of reality, but the limit of light's journey to us. Beyond it lies a universe that may extend much farther, perhaps infinitely, filled with galaxies, structures, and phenomena that we can never directly observe. The horizon, then, is a profound reminder that while we can study and comprehend an immense portion of the cosmos, there will always be realms that remain beyond our grasp, inspiring wonder and curiosity about what lies beyond the light we can see. One of the most counterintuitive yet fundamental truths about the universe is that it has no physical edge. Unlike a planet or a table, which has a definite boundary, the cosmos does not have a wall, cliff, or barrier where it ends. The universe, at least as far as we can tell, continues smoothly and seamlessly in every direction. The concept of an edge is something deeply rooted in everyday experience, but when it comes to the vast scale of the cosmos, such intuition no longer applies. Space itself is not bounded in the conventional sense. Even when we speak about the observable universe, it is critical to remember that this is defined by what light has had time to reach us, not by any limit in physical extent. Beyond the observable horizon, there may be an expanse of galaxies, clusters, and cosmic structures that extends endlessly. The observable universe is just a spherical volume surrounding Earth, where light has had enough time to travel since the Big Bang. The universe itself, however, is not confined to this sphere. It continues, and possibly stretches on infinitely, beyond our observational limits. The idea of no physical edge becomes easier to visualize when we think about the universe in terms of geometry rather than boundaries. In standard cosmological models, space can be flat, open, or curved. Observations, particularly measurements of the cosmic microwave background, suggest that space is remarkably flat on large scales. In a flat or open universe, there is no boundary where space stops. It simply continues indefinitely. Even in a curved, closed universe, space can loop back on itself, like the surface of a sphere. On a sphere, you can travel in one direction forever without encountering an edge. You simply return to your starting point. Similarly, in a closed universe, there could be no edge. The cosmos could wrap around itself in higher dimensional space. This lack of a physical edge is also implied by the cosmological principle, a cornerstone of modern cosmology. The principle states that the universe is homogeneous and isotropic on large scales, meaning that it looks the same everywhere and in all directions. If the universe were to have a wall or boundary, this uniformity would be violated. Instead, the universe appears smooth and continuous, suggesting that there is no end in the conventional sense, just regions beyond our observational reach. It is natural to imagine that if the universe has no edge, then traveling in any direction should eventually reveal a boundary. However, this is not the case. Even if we could move faster than any current technology allows, we would never encounter a wall. Space itself expands as we move through it. Galaxies recede not because they are moving through space, but because space is stretching. The more we observe or travel, the more we see the universe extending in all directions, and no matter how far we go, we would not encounter a barrier. The analogy of an inflating balloon can help illustrate this. Imagine tiny dots drawn on the surface of a balloon. As the balloon inflates, the dots move away from each other, but the surface itself has no edges. There is no point where the surface ends. Similarly, the universe expands, carrying galaxies apart, but there is no edge to reach. The dots, galaxies, move farther from each other, and space itself grows, but the universe has no wall or boundary. Every location in the universe can be thought of as the center of its own observational bubble, yet none of these points leads to a terminus. This absence of a physical edge is profound because it fundamentally changes how we perceive our place in the cosmos. We are not sitting inside a cosmic box, constrained by walls of space. we inhabit a universe that continues indefinitely in all directions. Our observable horizon might limit what we can see, but it does not define the extent of existence. Space itself is vast, unbounded, and continuous, extending far beyond the limits of human observation. It is also a reminder of the difference between perception and reality. Human intuition is shaped by bounded objects, tables, rooms, planets, but the universe does not conform to these intuitive notions. Infinity, continuity, and unboundedness are central features of the cosmos, challenging us to think beyond the familiar. There is no edge where the universe stops. There is only the ever-expanding expanse of space, stretching outward in all directions, carrying galaxies, stars, and planets along with it. Finally, the absence of a physical edge emphasizes that questions about where the universe ends are fundamentally different from questions about distance or horizon. The universe does not end, it continues, perhaps infinitely, regardless of what is observable. This understanding reframes our concept of size. The observable universe is just a tiny slice of reality, a window through which we glimpse a cosmos that may be much, much larger, or even infinite, without ever encountering a boundary or wall. A powerful way to visualize the expansion of the universe, and the absence of a physical edge, is through the classic balloon analogy. Imagine a balloon with tiny dots drawn on its surface. These dots represent galaxies, stars, or clusters of matter in the universe. As you begin to inflate the balloon, the surface stretches, and each dot moves away from all the others. Crucially, node is at the center of the expansion on the balloon's surface, and there is no edge to the surface itself. Every point moves away from every other point, and the space in between grows. This simple image captures the essence of cosmic expansion in a way that is intuitive, yet deeply revealing about the nature of the universe. In this analogy, it's important to note that the balloon's two-dimensional surface represents the three-dimensional space of the universe. We live in three spatial dimensions, so the universe does not expand into some higher dimensional outside, in the same way a balloon inflates into air around it. Instead, space itself stretches, increasing distances between galaxies. Just as the dots on the balloon move apart without ever reaching an edge of the surface, galaxies in the universe move apart as the fabric of space grows. No matter how far a galaxy moves, it does not encounter a boundary or wall. It simply continues to recede as space itself expands. The balloon analogy also highlights why every observer in the universe sees the same effect. If you were standing on one of the dots on the balloon's surface, it would appear as though every other dot were moving away from you. Similarly, no matter which galaxy we choose as a reference point, the expansion looks uniform. This explains why the universe appears isotropic, roughly the same in all directions, from every vantage point. The motion of galaxies is not due to them traveling through space, but because the surface they inhabit, space itself, is stretching, causing them to recede from one another. Another important aspect of this analogy is how it helps explain the apparent acceleration of expansion. Observations show that galaxies are not merely moving apart. The rate at which they recede from each other is increasing over time, driven by dark energy. On the balloon analogy, this is akin to inflating the balloon faster and faster. The dots move apart at an accelerating rate, even though they are stationary on the balloon itself. The space between them is stretching more rapidly, which mirrors the accelerating expansion of the universe. The analogy also emphasizes the absence of a central point. One common misconception is that the universe expands outward from a particular location, as if Earth or the Milky Way were the center of the cosmos. The balloon analogy corrects this intuition. No matter which dot you choose as your reference point, all other dots appear to move away. There is no unique center. The expansion occurs uniformly across the surface. In three-dimensional space, this means that the universe expands everywhere simultaneously, and every galaxy sees other galaxies receding, regardless of its position. Additionally, the analogy can help illustrate the concept of redshift. As the balloon stretches, the surface between the dots elongates. Similarly, as the fabric of space expands, light traveling through it is stretched, increasing its wavelength and shifting it toward the red end of the spectrum. This cosmological redshift is a direct consequence of expansion, analogous to how the distance between points on a balloon increases as the balloon inflates. The farther a galaxy is, the more its light is redshifted, just as dots that are farther apart on an inflating balloon move away faster. It's also useful for visualizing the difference between the observable and unobservable universe. On the balloon, imagine that you can only see a small patch of the surface due to fog or some limitation of vision. You perceive a finite area and can measure distances within it. But you know the surface continues beyond your view. Similarly, the observable universe is a finite region determined by the travel time of light, while the unobservable universe may extend indefinitely. The balloon's surface has no edge, yet our perspective is limited to the patch we can observe, a direct parallel to the cosmos. Finally, the balloon analogy reinforces the idea that space itself is dynamic. Galaxies are not simply drifting through a pre-existing void. The very fabric of the universe stretches, and this stretching shapes distances, observations, and the evolution of cosmic structures. The universe's expansion, the acceleration due to dark energy, and the cosmological redshift are all direct consequences of this dynamic nature. The analogy may be simple, but it conveys one of the deepest truths about the cosmos. The universe grows everywhere, with no center, no edge, and no limit in sight. By picturing galaxies as dots on an inflating balloon, we gain an intuitive grasp of why galaxies move apart, why space can stretch without a boundary, and why the observable universe is just a small window into a potentially infinite cosmos. It is a visualization that bridges human understanding with cosmic reality, offering a glimpse into a universe that is both elegant and incomprehensibly vast. Galaxies serve as the perfect markers for visualizing the expansion of the universe, much like the dots on the surface of an inflating balloon in the analogy we just discussed. Each galaxy is not only a vast collection of stars, planets, gas, and dark matter, but also a fixed point in the fabric of space. As space itself expands, galaxies are carried apart from one another, not because they are moving through space in the conventional sense, but because the stage of the universe, the very fabric of space-time, is stretching. This movement is a key observation in cosmology and provides crucial evidence for the dynamic, evolving nature of the universe. When we look at the night sky, the stars within our own Milky Way are bound by gravity and do not participate in this large-scale cosmic expansion. However, other galaxies, especially those outside our local group, drift away from us over time. Their motion is not like that of a car traveling along a road, but is instead the result of the expansion of space itself. Every galaxy essentially rides along a stretching grid of space-time, much like dots glued onto a balloon's surface move apart as the balloon inflates. The farther two galaxies are from each other, the faster they appear to recede, which is exactly what astronomers observe and what underpins Hubble's law. The analogy of galaxies as dots also helps illustrate why the expansion is uniform on large scales. Regardless of which galaxy you choose as a reference point, all others seem to move away from it. This is because the expansion of space is not centered on any particular galaxy. It is a property of the universe as a whole. Every galaxy participates in this expansion equally, making it appear as if every observer is at the center of the cosmic retreat. This principle helps explain the isotropic nature of the universe. On a sufficiently large scale, the cosmos looks the same in every direction. Galaxies also provide a practical tool for measuring cosmic expansion. By observing the light emitted from galaxies and analyzing the degree to which it is redshifted, astronomers can determine how fast these galaxies are receding. The redshift increases with distance, reflecting how the expansion stretches the wavelength of light over time. In this sense, galaxies act as natural markers, each carrying information about the universe's growth, its history, and the influence of dark energy on the rate of expansion. The distribution of galaxies also reveals the large-scale structure of the cosmos. Far from being randomly scattered, galaxies form an intricate cosmic web of clusters, filaments, and voids that spans billions of light-years. Galaxies highlight the patterns in the universe's evolution. Dense clusters show regions of intense gravitational attraction, while vast voids illustrate areas where matter is sparse. By tracking how galaxies move and are spaced apart, we gain insight not only into the expansion of space but also into the formation and evolution of cosmic structures over billions of years. It's important to note that while galaxies serve as markers, the space between them contains dark energy, dark matter, and sparse intergalactic gas. Dark energy, which drives the accelerated expansion of the universe, affects the distances between galaxies, stretching space ever more rapidly. The galaxies themselves act as visible reference points in this otherwise invisible dynamic, providing the dots that allow us to map the universe's growth across time. Without galaxies, the expansion would be far more abstract and difficult to quantify, as we rely on these luminous beacons to track motion across unimaginable distances. Galaxies also reinforce the concept of the observable versus unobservable universe. We can detect and study galaxies within our observable horizon, tracing light that has traveled billions of years. Beyond that, galaxies may exist in regions that are forever beyond our observational reach due to the limits imposed by light travel and cosmic expansion. These unobservable galaxies would continue to move apart in the same way, carrying the cosmic story forward even if we can never witness it directly. Furthermore, galaxies provide a temporal dimension to our understanding of the universe. Because light takes time to travel, observing distant galaxies allows us to see them as they were billions of years ago. Each galaxy is not just a marker of spatial distance but also a record of cosmic history. By studying the distribution, composition, and motion of galaxies, astronomers reconstruct the universe's past, understand the formation of large-scale structures, and predict future evolution. The galaxies themselves become chronometers of cosmic time, their light stretching across the expanding space like threads weaving the story of the universe. The image of galaxies as dots on a balloon helps reconcile many abstract concepts. It visually demonstrates why galaxies move apart without a central explosion, why there is no edge, and why the universe appears uniform from any vantage point. It emphasizes that cosmic expansion is a property of space itself, not of the galaxies individually. And it reminds us that while galaxies may seem static in the night sky on human timescales, on cosmic timescales, they are part of a grand, dynamic dance, carried apart across the ever-expanding fabric of the cosmos. One of the most profound discoveries in modern cosmology is that the expansion of the universe is not slowing down, as once expected, but accelerating. This unexpected acceleration points to a mysterious and invisible force known as dark energy, which permeates all of space and dominates the universe's dynamics. Dark energy is not a type of matter or radiation. Rather, it is a property of space itself, exerting a repulsive effect that pushes galaxies apart and causes the expansion of the universe to speed up over time. It is perhaps the most enigmatic component of the cosmos, constituting roughly 68% of the total energy content of the universe, yet remaining entirely undetectable except through its gravitational influence on cosmic expansion. The existence of dark energy was first inferred in the late 1990s through observations of distant Type Ia supernovae, which are stellar explosions that serve as standard candles for measuring cosmic distances. Astronomers expected that the universe's expansion would be slowing under the pull of gravity from all the matter in the cosmos. Instead, they observed that these supernovae appeared fainter than expected, indicating that the galaxies hosting them were farther away than predicted by models of decelerating expansion. This implied that the expansion of the universe was accelerating, revealing the presence of a previously unknown form of energy, dark energy. Dark energy is fundamentally different from ordinary matter or dark matter. While matter, whether visible or dark, gravitates and pulls other matter together, dark energy behaves as a repulsive force. Its effect is uniform across space, meaning it does not clump into galaxies or clusters but instead acts throughout the cosmos, stretching space itself. As the universe expands, the influence of dark energy grows in importance because matter and radiation become less dense over time, while dark energy maintains a roughly constant density. This explains why the acceleration of expansion becomes more pronounced as the universe ages. Understanding dark energy requires a departure from intuition. We are used to thinking of forces as pushing or pulling objects through space, but dark energy acts differently. It changes the very fabric of space. Imagine space as a rubber sheet. Dark energy is like a property of the sheet that causes it to stretch more and more over time, regardless of what is on the sheet. Galaxies, stars, and planets are carried along with this stretching, not because they are being pushed by a force in the usual sense, but because the space between them is growing. This makes dark energy not only a cosmic mystery but also a profound departure from classical physics. The influence of dark energy is responsible for several remarkable features of the universe we observe today. First, it determines the ultimate fate of cosmic expansion. If dark energy continues to dominate, the universe will expand forever, with galaxies moving farther apart and the cosmos becoming increasingly cold, dark, and diffuse. In this scenario, eventually, most galaxies will recede beyond our observable horizon, leaving isolated pockets of matter in an ever-expanding void. This scenario is sometimes referred to as the Big Freeze or heat death of the universe. Dark energy also shapes the geometry and large-scale structure of the universe. Its repulsive effect influences how galaxies and clusters distribute themselves, the formation of cosmic voids, and the evolution of superclusters over billions of years. While matter provides gravitational attraction that pulls structures together, dark energy counteracts this pull on large scales, leading to the observed accelerated expansion and the continued stretching of space between distant galaxies. Despite its critical role, dark energy remains one of the greatest unsolved mysteries in science. Physicists have proposed various explanations, ranging from a cosmological constant, a uniform energy density inherent to space itself, as originally suggested by Einstein, to dynamic fields that evolve over time, sometimes called quintessence. Each model attempts to explain why dark energy has the value it does and why it becomes dominant precisely at the epoch we observe. Yet, no explanation has been definitively confirmed, and direct detection of dark energy remains beyond current technology. Dark energy also challenges human intuition and philosophy. Unlike matter, which can be seen, touched, or weighed, dark energy is invisible, intangible, and indirectly inferred from its effects on space and galaxies. It highlights the idea that the universe is governed by forces and phenomena far beyond our everyday experience. The accelerating expansion it drives underscores the dynamic, ever-changing nature of the cosmos, in contrast to a static, eternal universe that seemed plausible before these discoveries. Furthermore, dark energy interacts with our understanding of the observable universe and the cosmic horizon. As expansion accelerates, the effective observable volume shrinks in terms of future accessibility. Galaxies that are currently visible may eventually move beyond our horizon, disappearing from view as space expands faster than light can traverse it. In this way, dark energy not only shapes the universe's present but also defines the ultimate limits of what we can ever see or know. Ultimately, dark energy reminds us that the universe is not only vast but also mysterious. It drives the accelerated expansion of space, shapes the evolution of cosmic structures, and hints at the profound complexity underlying reality itself. Galaxies are markers riding on the currents of space, and dark energy is the unseen force accelerating those currents, propelling the cosmos into an ever-expanding future that continues to challenge our understanding. The fate of cosmic expansion is one of the most profound questions in all of astronomy and cosmology, and it is deeply tied to the presence of dark energy. Observations over the past few decades have revealed that the universe is not only expanding, but that this expansion is accelerating. This acceleration implies that, unless something dramatic changes in the future, the universe will continue to expand indefinitely, growing larger and more diffuse over time. The long-term implications of this ongoing expansion are both astonishing and humbling, reshaping our understanding of the cosmos and our place within it. If the current acceleration continues, the scale of the universe will increase exponentially. Galaxies that are not gravitationally bound to one another, meaning they are not part of clusters or groups held together by mutual gravity, will recede from each other at ever-increasing speeds. Over tens of billions of years, these galaxies will move so far apart that their light will no longer reach us, effectively disappearing beyond our cosmic horizon. From a local perspective, the universe would appear emptier and darker, with distant galaxies vanishing from view, leaving only the remnants of gravitationally bound structures, such as the Milky Way and its nearest companions. This scenario, sometimes referred to as the Big Freeze or heat death, is a direct consequence of accelerated expansion. As space stretches, the density of matter decreases, the temperature of the universe falls, and stars eventually burn out. Black holes, the last remaining sources of energy, will slowly evaporate over unimaginable timescales via Hawking radiation. In this far future, the universe becomes cold, dark, and isolated, with cosmic structures drifting apart in a vast, nearly empty space. The expansion continues relentlessly, driven by dark energy, which maintains or increases its dominance over gravitational forces. The idea that expansion might continue forever also challenges our human intuition about scale and time. Today, we talk about billions of light-years and billions of years, numbers that already feel almost incomprehensible. But in a perpetually expanding universe, these scales become even more extreme. The distances between galaxies will grow beyond anything we can realistically visualize, and regions that are currently part of the observable universe may slip out of reach entirely. Over tens or hundreds of billions of years, the observable universe itself could shrink relative to any given point, because more and more light-emitting objects will move beyond our horizon. The permanence of expansion also reinforces the notion that the universe has no center and no edge. As space expands, every point experiences the same effect. All other points move away. The expansion does not occur from a central point. It occurs everywhere at once. This continuous, uniform growth makes the universe larger than any conceivable boundary or container. Even if we could travel endlessly in any direction, there would be no final wall, no edge to reach. Space itself is stretching, carrying galaxies with it, and the size of the universe increases indefinitely. Furthermore, the prospect of eternal expansion has implications for the large-scale structure of the universe. Over immense timescales, gravitationally unbound structures will be carried apart, leaving isolated clusters and superclusters. The intricate cosmic web of filaments and voids that we observe today will become less connected, as the distance between major structures grows ever greater. Eventually, the universe may consist of isolated island universes, surrounded by vast expanses of dark, empty space, each one increasingly unreachable from the others. This continuous growth also amplifies the role of dark energy. As matter becomes less dense, dark energy comes to dominate the dynamics of the universe even more completely. Its effect ensures that expansion accelerates rather than slows down, pushing distant galaxies ever faster beyond the reach of observation. The universe is not simply getting bigger in a linear sense. It is growing at an accelerating rate, making the distances involved increasingly difficult to conceptualize. On a philosophical level, the notion that expansion may continue forever challenges human notions of permanence and scale. The universe is not static, and it will not settle into a final, unchanging state in the near future. Instead, it is dynamic, vast, and potentially boundless, with distances and timescales that dwarf any human reference point. The cosmos becomes a place of perpetual change, where even structures that seem permanent today, galaxies, clusters, and superclusters, are ultimately temporary in the grand scope of expansion. In practical terms, eternal expansion also sets a limit on what future civilizations, if any exist, might be able to observe. As the expansion progresses, more of the universe will slip beyond the cosmic horizon, effectively reducing the volume of space accessible to observation. Civilizations in the far future may live in an apparently empty universe, unaware of the billions of galaxies that were once visible, highlighting the profound temporal dimension of cosmology. The universe's size is not only spatial but also a function of cosmic time. In sum, the ongoing and potentially eternal expansion of the universe ensures that it will continue to grow far beyond what we can currently imagine. Galaxies will drift apart, cosmic structures will become increasingly isolated, and the observable universe will shrink relative to the ever-expanding totality of space. The universe's fate, dictated by dark energy and the expansion of space-time, is a cosmos that becomes larger, emptier, and more diffuse over time, a vast and dynamic reality that stretches human comprehension to its limits. The cosmic microwave background, or CMB, is one of the most remarkable discoveries in cosmology and serves as a direct window into the earliest moments of the universe. It is essentially the faint afterglow of the Big Bang, the radiation left over from a time when the universe was hot, dense, and opaque, a period approximately 380,000 years after the initial explosion of energy and matter that began the cosmos as we know it. The CMB is the oldest light we can detect, representing the furthest signal that has ever reached us and providing a snapshot of the universe at an epoch before stars, galaxies, or even atoms in their familiar form existed. The origin of the CMB lies in the early universe, when it was filled with a plasma of protons, electrons, and photons. In this primordial soup, photons, the particles of light, could not travel freely because they were constantly scattered by the charged particles around them. This made the early universe opaque, like a dense fog. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms in a process known as recombination. This dramatically reduced the scattering of photons, allowing light to travel freely through space for the first time. These photons, stretched to longer wavelengths by the expansion of the universe over billions of years, now reach us as microwave radiation, the cosmic microwave background. The CMB is incredibly uniform across the sky, with variations in temperature on the order of just 1 part in 100,000. These tiny fluctuations are not random. They encode a wealth of information about the early universe. They reveal the seeds of the large-scale structures we see today: galaxies, clusters, and superclusters, that grew from slight differences in density under the influence of gravity. By mapping these fluctuations, cosmologists can reconstruct the universe's geometry, composition, and rate of expansion, making the CMB a cornerstone of modern cosmology. What makes the CMB especially significant is that it is, in a sense, the ultimate boundary of observable light. Unlike light from distant galaxies, which has traveled across billions of years but originates from objects formed long after the Big Bang, the CMB comes from the very epoch when the universe first became transparent. We cannot see beyond it using traditional electromagnetic radiation because before recombination, photons were trapped in the plasma. The CMB therefore represents the furthest back in time we can observe using light, marking the surface of last scattering. Beyond this surface, the universe was opaque to radiation, making it inaccessible to direct optical observation. The detection of the CMB in 1965 by Arno Penzias and Robert Wilson was a pivotal moment in physics, confirming the Big Bang theory over competing models of the universe. Its existence showed that the universe had a hot, dense origin and had been cooling over time as it expanded. Today, highly sensitive satellites like COBE, WMAP, and Planck have mapped the CMB with exquisite precision, revealing subtle patterns and polarization that provide insights into the universe's age, composition, and rate of expansion. The CMB has allowed cosmologists to estimate the universe's age at approximately 13.8 billion years, measure the density of matter and dark energy, and confirm the flatness of space on cosmic scales. Observing the CMB also illustrates a critical concept in cosmology. Looking at distant objects is equivalent to looking back in time. While galaxies billions of light-years away show us snapshots of cosmic history, the CMB shows the universe as it was almost 13.8 billion years ago, at a time before stars or galaxies existed. It is the ultimate time capsule, a relic from the earliest observable epoch, carrying information about the conditions and dynamics of the young cosmos. The CMB also provides a framework for understanding the limits of our telescopes and observational techniques. While we can observe galaxies across the observable universe, no electromagnetic signal from earlier epochs can reach us because space was opaque prior to recombination. In this sense, the CMB represents a natural observational horizon. Although future instruments may allow us to detect gravitational waves or neutrinos from earlier times, traditional light-based observation cannot probe beyond the surface of last scattering. Furthermore, the CMB is critical for understanding cosmic expansion and dark energy. By measuring the fluctuations and patterns in the microwave background, cosmologists can infer how the universe has expanded since its early stages. Comparing these measurements with observations of distant supernovae and galaxy clusters provides strong evidence for the accelerated expansion driven by dark energy. In this way, the CMB is not only a record of the early universe but also a tool for probing the ongoing evolution and ultimate fate of the cosmos. In essence, the cosmic microwave background represents the furthest light signal we can observe, a relic of the universe's earliest moments and a direct connection to the Big Bang itself. It is a faint glow that permeates the entire sky, invisible to the naked eye but detectable with sensitive instruments, and it serves as a fundamental reference point for understanding the age, composition, and evolution of the universe. The CMB is a constant reminder that while the universe is vast and expanding, it carries with it the imprints of its origins, encoded in the oldest light that ever traveled across space. One of the most fascinating aspects of observing the universe is that looking at distant galaxies is, in essence, looking back in time. Because light travels at a finite speed, roughly 299,792 kilometers per second, when we observe an object, we are seeing the light it emitted in the past. The farther away a galaxy is, the longer its light has traveled to reach us. This principle transforms astronomy into a cosmic time machine, allowing us to study the history of the universe across billions of years simply by observing distant objects in the night sky. For example, when we observe our closest large neighbor, the Andromeda Galaxy, we are seeing it as it was about 2.5 million years ago. That may seem short in cosmic terms, but when we look at galaxies millions or billions of light-years away, the temporal difference becomes profound. A galaxy 1 billion light-years distant appears to us as it existed 1 billion years in the past. The light we receive today left that galaxy long before our own solar system had fully formed. In effect, every observation is a glimpse into a previous epoch, a historical record of the cosmos preserved in photons that have traversed unimaginable distances. This look-back time is essential for understanding cosmic evolution. By observing galaxies at various distances, astronomers can reconstruct how galaxies form, evolve, and interact over billions of years. We can see galaxies in their youth, when star formation rates were higher and structures were less developed, and compare them with older, more mature galaxies closer to us. This allows scientists to piece together a chronological narrative of galaxy formation, star birth, and the assembly of cosmic structures over the entire history of the universe. The concept also applies to other cosmic phenomena. Quasars, the extremely luminous cores of distant galaxies powered by supermassive black holes, are visible as they existed billions of years ago, often from a time when the universe was only a fraction of its current age. Gamma-ray bursts, exploding stars, and other energetic events are captured in our telescopes not as they are today, but as they happened in the distant past. Observing these phenomena allows astronomers to trace the physical processes shaping the universe at every stage of its history. One particularly striking implication of looking back in time is that we are witnessing cosmic conditions that no longer exist. Many of the galaxies we see at extreme distances have long since evolved or merged into other structures. Stars have formed, died, and exploded in supernovae. Black holes have grown, and entire galactic clusters have shifted. The light arriving at our telescopes is essentially a snapshot frozen in time, a record of the universe as it was when that light was emitted. Each photon is a messenger from the past, carrying information about conditions, composition, and motion billions of years ago. Looking back in time also allows us to study the early universe near the cosmic microwave background. While the CMB represents the farthest observable signal in terms of light, the galaxies we observe billions of light-years away provide a continuous record bridging the gap between the primordial epoch and the present day. Observing distant galaxies allows astronomers to track the growth of structure, the evolution of chemical elements, and the influence of dark matter and dark energy on cosmic expansion. Every distant galaxy is a piece of a vast historical puzzle, enabling us to reconstruct the universe's evolutionary trajectory. This temporal perspective also reshapes our understanding of scale and distance. Light-years, by definition, are not just measures of distance but also measures of time. A galaxy 1 billion light-years away is both spatially distant and temporally ancient. In this sense, astronomy is inherently historical. Observing distant objects is synonymous with studying the universe's past. The farther we look, the deeper into cosmic history we peer, ultimately approaching the initial conditions of the Big Bang itself. Moreover, the concept of looking back in time underscores the finite nature of our observational universe. Because light takes time to travel, there is a limit to how far back we can see, the surface of last scattering represented by the cosmic microwave background. Beyond this point, the universe was opaque to photons, and no light from earlier epochs reaches us. Thus, every observation is a journey backward in time, constrained by the finite speed of light and the age of the cosmos, highlighting both the power and limits of our ability to probe the universe's history. Finally, this principle instills a sense of connection to the vastness of cosmic time. When we observe distant galaxies, we are engaging directly with the universe's history, witnessing events that occurred long before humans existed on Earth. It is a humbling and awe-inspiring reminder that the cosmos has a narrative far greater and older than any individual existence. Each photon that reaches us from billions of light-years away is a storyteller, conveying the universe's epic journey across space and time. In essence, looking at distant galaxies is not just about mapping space, it is about mapping time itself. Every observation is a glimpse into the past, a window into the universe's history, and a direct encounter with epochs that have long since passed. The farther we look, the more we travel back, approaching the very origins of the cosmos and gaining insight into how the universe evolved into the vast, complex, and dynamic entity we inhabit today. Even the most advanced telescopes have fundamental limits when it comes to observing the universe, and these limits are dictated not by technological shortcomings but by the physics of the cosmos itself. The farthest we can see using light, whether visible, infrared, radio, or other electromagnetic waves, is the cosmic microwave background, CMB, the faint afterglow of the Big Bang. This makes the CMB a natural observational frontier, beyond which traditional telescopes cannot peer. The universe before the CMB existed in a state that was opaque to light, meaning photons could not travel freely. As a result, no amount of optical or infrared sensitivity can allow us to observe events earlier than this epoch. The light simply never escaped to reach us. This limitation is intrinsic to the early universe. Prior to about 380,000 years after the Big Bang, the cosmos was a hot, dense plasma composed of protons, electrons, and photons. The constant scattering of photons off charged particles prevented light from traveling any significant distance, effectively trapping it. Observing this period directly with light is impossible because there were no freely moving photons to carry information to us. The CMB represents the point at which the universe cooled enough for neutral atoms to form, a process called recombination, allowing photons to travel unimpeded. It is the earliest snapshot of the universe that can be observed using electromagnetic radiation. Even with revolutionary instruments like the Hubble Space Telescope, the James Webb Space Telescope, or highly sensitive ground-based radio and submillimeter observatories, our observations are confined by this boundary. We can study galaxies forming just a few 100 million years after the Big Bang, but we cannot see the first moments of the universe's existence in light. What telescopes allow us to do is probe closer and closer to the CMB, revealing the structure and evolution of early galaxies, star formation, and the growth of large-scale cosmic structures, but there is a hard observational ceiling imposed by physics. This limitation underscores the distinction between observational constraints and the actual size or extent of the universe. The observable universe is defined not by the totality of space but by the reach of light and other signals that have had time to travel to Earth. There may be regions of the universe far beyond our observational horizon, perhaps infinitely distant, which will never be accessible with light-based instruments. Even the most powerful telescopes cannot overcome the finite speed of light or the opacity of the primordial universe prior to the CMB. However, while telescopes are constrained in observing the earliest photons, scientists have developed alternative ways to probe the universe's history before the CMB. For instance, gravitational waves and neutrinos could, in principle, carry information from epochs inaccessible to light. Gravitational waves, ripples in the fabric of spacetime, can propagate freely through the dense early universe, offering a potential window into the moments immediately following the Big Bang. Neutrinos, nearly massless and weakly interacting, could also traverse the early plasma without scattering. These avenues remain largely theoretical at present, but they illustrate that our understanding of the universe is not limited solely by telescopes, even though electromagnetic observation has a hard limit at the CMB. The limitations of telescopes also highlight the importance of technological advancements and innovative observation strategies. Infrared telescopes, like the James Webb Space Telescope, allow us to peer farther back in time than visible light instruments, because the light from the earliest galaxies is redshifted into longer wavelengths due to cosmic expansion. Radio telescopes can detect hydrogen emission from very distant epochs, providing indirect information about the universe's structure near the CMB. But all these approaches still converge on the same fundamental boundary, the CMB itself. Beyond it, there are no photons to observe. Recognizing this limit provides perspective on how much we can actually know about the universe. Despite tremendous advances in astronomy, our direct view of the cosmos is bounded by a natural horizon. The observable universe is immense, stretching 46 billion light-years in every direction, yet it remains only a finite portion of what likely exists. Even with perfect technology, we cannot see past the CMB with light. The universe before recombination is hidden from direct optical or infrared observation. This limitation is a humbling reminder that no matter how sophisticated our instruments become, there will always be aspects of the cosmos that remain forever beyond human perception. Extensive galaxy surveys. Projects like the Sloan Digital Sky Survey, SDSS, and the 2DF Galaxy Redshift Survey have charted millions of galaxies, revealing the cosmic web in remarkable detail. These surveys show that galaxies are not uniformly distributed. Instead, they trace out the filamentary patterns predicted by theoretical models of cosmic structure formation. Superclusters, such as the Laniakea supercluster that includes the Milky Way, are immense knots within this web, comprising thousands of galaxies bound together by gravity. The cosmic web is also dynamic. Galaxies within filaments can move along these structures, gradually merging into larger clusters over billions of years. This ongoing evolution is driven by gravitational attraction, the expansion of the universe, and the influence of dark energy. As space expands, distant filaments and clusters drift apart, but the internal dynamics within clusters and filaments continue to shape the local distribution of galaxies. Over time, the cosmic web becomes more diffuse on the larger scales due to the accelerating expansion of the universe, even as structures within it continue to evolve and interact. On the largest scales, the universe exhibits a remarkable degree of isotropy and homogeneity. While the cosmic web is highly structured locally, when averaged over hundreds of millions of light-years, the universe appears uniform. This balance between local clumpiness and large-scale uniformity is a fundamental feature of cosmology and underpins models of cosmic evolution. It also supports the cosmological principle, which posits that the universe looks roughly the same from any vantage point on sufficiently large scales. The cosmic web also provides a framework for understanding the distribution of matter and the role of dark matter and dark energy. Filaments of the web are dominated by dark matter, which makes up the majority of mass in the universe. The gravitational pull of dark matter shapes the formation and growth of galaxies, guiding their locations along the filaments and toward the dense nodes of clusters. Dark energy, on the other hand, drives the accelerated expansion of space, stretching the distances between these structures and influencing the large-scale evolution of the web. Visualizations of the cosmic web are both scientifically valuable and aesthetically striking. Simulations of the universe, such as those from the Millennium Simulation and Illustris projects, recreate the cosmic web with remarkable accuracy, showing galaxies, dark matter filaments, and voids distributed across a vast, three-dimensional network. These simulations match observations closely, confirming our understanding of how matter organizes itself under gravity over billions of years. They also emphasize the vastness of cosmic structures, stretching across scales that dwarf individual galaxies or clusters. Ultimately, the cosmic web reveals the universe as a vast, interconnected network, with galaxies serving as luminous markers of an underlying gravitational framework dominated by dark matter. Filaments, clusters, and voids together create a structure that extends across billions of light-years, connecting regions of space that appear isolated to the naked eye. The large-scale structure of the universe provides insight not only into how matter is distributed but also into the processes that have shaped cosmic evolution, from the earliest density fluctuations to the ongoing expansion driven by dark energy. The sheer scale of the universe is truly staggering, and one of the most difficult aspects for humans to grasp is just how large distances in cosmology really are. When we talk about billions of light-years, we are operating at a scale far removed from everyday human experience, where even thousands of kilometers or miles feel immense. 1 light-year, the distance light travels in a single year, is roughly 9.46 trillion kilometers, or about 5.88 trillion miles. Multiply that by a billion, and the numbers quickly become so enormous that they defy intuitive comprehension. When astronomers say that a galaxy is 10 billion light-years away, they are describing a distance that is both almost unimaginably vast and temporally profound, because we are seeing that galaxy as it was 10 billion years ago, early in the universe's history. To attempt to picture a billion light-years is to push the boundaries of imagination. The observable universe has a radius of approximately 46 billion light-years, meaning light from the most distant galaxies we can see has traveled across a distance that is almost beyond human understanding. To provide some perspective, if the Earth was shrunk to the size of a grain of sand, the Milky Way galaxy would be roughly the size of the United States. Scaling up further, the distance to the nearest large galaxy, Andromeda, would be akin to the space between New York and Los Angeles. Now imagine stretching that analogy to encompass the billions of galaxies across the observable universe. The scale becomes truly mind-boggling. Even attempts to quantify these distances in more familiar units struggle to convey the enormity. For instance, the light from the Sun takes about 8 minutes to reach Earth. Light from the nearest star beyond the Sun, Proxima Centauri, takes 4.24 years to arrive. Now multiply that by millions or billions, and you reach distances that are almost meaningless in any human context. Distances of hundreds of millions of light-years separate galaxy clusters, while superclusters and filaments span billions of light-years. These distances are so extreme that any concept based on human experience, walking, driving, flying, becomes entirely inadequate. We can describe the numbers mathematically, but truly picturing them is virtually impossible. Even time adds another layer of incomprehensibility. When we observe a galaxy a billion light-years away, we are looking a billion years into the past. For comparison, the entire span of human civilization is only a few thousand years old. The light we see from distant galaxies has been traveling for periods of time that dwarf the entire history of humanity. Galaxies that appear near each other in the sky may actually be separated by distances so vast that light from one has taken billions of years longer to reach us than light from another. Thinking in terms of both distance and time simultaneously stretches the mind, challenging the very way we intuitively understand space. Even within our own galaxy, distances are enormous by human standards. The Milky Way is about 100,000 light-years across, meaning light itself would take 100,000 years to cross it. Yet, compared to the cosmic scale, this is tiny. When considering the distance between superclusters or the largest filaments of the cosmic web, we are dealing with lengths hundreds of times greater than the diameter of the Milky Way. The voids between filaments, vast expanses of nearly empty space, can span hundreds of millions of light-years, emphasizing that even empty space contains distances that are hard to comprehend. To further illustrate, consider traveling at the speed of the fastest spacecraft humanity has built, roughly 70,000 kilometers per hour. At this speed, it would take tens of millions of years just to reach the nearest star outside our solar system. Reaching a galaxy a billion light-years away would take a duration so extreme that it becomes meaningless in human terms. Distances in billions of light-years are therefore not just large, they are orders of magnitude beyond any conceivable scale of daily life. Even mathematical abstractions struggle to communicate the enormity, leaving our minds to rely on analogies or visualizations that can only hint at the true scope. This incomprehensible scale also emphasizes the limitations of human perception. Our senses evolved to navigate a world measured in meters and kilometers, not light-years and megaparsecs. Concepts like billions or tens of billions of light-years are abstract. We can perform calculations, create maps, and even generate simulations, but they remain fundamentally removed from tangible experience. The universe operates on scales that are almost entirely outside the realm of intuition, requiring us to think in terms of mathematics, physics, and visualizations rather than sensory experience. In practical terms, astronomers use these massive distances to categorize and organize the cosmos. Distances help define epochs in cosmic history, establish the size of large-scale structures, and measure the effects of cosmic expansion. Yet the numbers themselves remain almost impossible to internalize. A galaxy observed at 10 billion light-years is both spatially and temporally distant, and even imagining the light traveling uninterrupted for 10 billion years strains comprehension. The human mind can understand the principle but struggles to feel the scale, highlighting how extraordinary and humbling the universe truly is. In essence, distances measured in billions of light-years represent a scale that surpasses ordinary intuition. They encompass time periods vastly longer than human history and spaces far larger than anything experienced on Earth. These numbers remind us of our relative smallness in the cosmos and the profound vastness of the universe, stretching across scales that challenge both understanding and imagination. They are a testament to the mind-boggling size of the cosmos and a reminder that the universe operates on a scale almost impossible for us to truly grasp. To help grasp the unfathomable scale of the universe, comparisons and analogies are essential, because raw numbers, billions of light-years, trillions of galaxies, can be almost meaningless without context. One of the most striking comparisons is the realization that our Milky Way, the galaxy we call home, is merely one of perhaps 2 trillion galaxies in the observable universe. Each of these galaxies contains hundreds of billions of stars, many with their own planetary systems, stretching across distances unimaginable in human terms. The sheer number of galaxies, let alone stars and planets, is almost impossible to truly visualize. Yet making comparisons can help bring some perspective to these cosmic quantities. Consider the Milky Way itself. It is roughly 100,000 light-years in diameter and contains around 200 to 400 billion stars. If the Sun were reduced to the size of a single grain of sand, the Milky Way would span several continents. Yet, when we compare this to the nearest galaxy, Andromeda, located about 2.5 million light-years away, or to distant galaxies billions of light-years away, even the size of our galaxy becomes a tiny fraction of cosmic distances. Now, when multiplied across billions of galaxies, each containing hundreds of billions of stars, the universe becomes a place of almost incomprehensible richness and vastness. To imagine the scale of galaxies across the cosmos, consider this analogy. If the Milky Way were a single apple, then a neighboring galaxy like Andromeda would be another apple placed 25 kilometers away. Galaxies in distant clusters might be hundreds or thousands of kilometers away in this analogy, and the full observable universe would extend so far that it would stretch across an entire continent, or even a planet, covered with billions of apple galaxies. This gives a sense of both the incredible number of galaxies and the enormous spaces that separate them. Another way to frame it is by comparing stars to grains of sand. If each star in the Milky Way were represented by a single grain of sand, then each galaxy would be a vast beach, and the observable universe would be composed of trillions of such beaches, spread across cosmic deserts of nearly empty space. These analogies attempt to make the mind-boggling numbers more tangible, yet they also underscore how ordinary human scales are inadequate for understanding the universe's enormity. The concept of cosmic neighborhoods also helps provide context. Our solar system is part of the Milky Way, which is itself part of the local group, a cluster of about 50 galaxies bound together by gravity. The local group is in turn part of the Virgo supercluster, which is itself a component of the even larger Laniakea supercluster. Each step outward in this hierarchy emphasizes both the richness of the universe and the relative insignificance of any single galaxy or cluster. While the Milky Way seems enormous from our perspective, it is just a tiny component of a structure spanning hundreds of millions of light-years. To make the scale even more striking, consider human history in comparison. The age of the universe is about 13.8 billion years. If the entire history of the cosmos were compressed into a single calendar year, with the Big Bang occurring on January 1st, modern humans would not appear until late on December 31st, and the entirety of recorded human history would occupy just a few seconds before midnight. Galaxies, stars, and cosmic structures have existed for billions of years before our species even appeared, emphasizing the immense scales of both space and time that define the universe. Even within galaxies, the numbers are staggering. Our Milky Way contains hundreds of billions of stars, many of which may host planets. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away, a trivial distance on cosmic scales, yet still almost incomprehensibly far in human terms. Multiply this across trillions of galaxies, each containing billions of stars, and the scale becomes almost impossible to picture. Comparisons, analogies, and hierarchical structures help us frame these numbers, but they can never fully convey the immensity of the cosmos. Another analogy comes from considering distances in terms of travel time. Light from the Andromeda galaxy takes 2.5 million years to reach us. Light from galaxies near the edge of the observable universe has been traveling for almost 13.8 billion years. If you attempted to traverse these distances at the speed of the fastest spacecraft ever built by humans, it would take millions or even billions of years to reach a single galaxy. This kind of comparison highlights both the vastness of space and the limits of human perception when attempting to conceptualize cosmic scales. Finally, analogies help illustrate the contrast between the observable universe and the likely totality of the cosmos. The observable universe contains perhaps 2 trillion galaxies, yet this may be just a tiny fraction of what exists beyond our observational horizon. The universe beyond what we can see could be unimaginably larger, perhaps infinite, making our local cosmic neighborhood, the Milky Way, the local group, the Virgo supercluster, tiny dots in an almost limitless expanse. Comparisons like this help us begin to appreciate the enormity of the universe, even if they fall short of fully capturing its scale. In essence, comparisons allow us to conceptualize the vast numbers involved in cosmology. Our Milky Way is just one of trillions of galaxies, each with hundreds of billions of stars. Distances between galaxies span millions to billions of light-years. Cosmic time stretches billions of years into the past. These analogies help ground human understanding in something relatable, yet they also highlight the humility and/or inspired by the universe's vastness. The cosmos is not only enormous, it is structured, ancient, and filled with complexity that dwarfs any human scale. When we place humanity within the context of the universe, our scale becomes almost inconceivably small. Earth, with its oceans, continents, and biosphere, is our entire world, a fragile sphere roughly 12,742 kilometers in diameter. It seems vast from a human perspective. We traverse it in hours by plane or months by ship, and we measure our civilization in millennia. Yet when set against the cosmic backdrop of the Milky Way, let alone the billions of galaxies in the observable universe, Earth is virtually a speck, a microscopic dot suspended in a vast expanse of space. The contrast between human scale and cosmic scale serves to inspire awe, humility, and a profound sense of wonder. Even within the solar system, Earth is dwarfed by its neighbors. Jupiter, the largest planet in our system, has a diameter over 11 times that of Earth and a volume that could contain more than 1,000 Earths. The Sun, a single star among hundreds of billions in the Milky Way, has a diameter roughly 109 times that of Earth and contains 99.86% of the solar system's mass. Distances in the solar system are vast enough that light takes over 8 minutes to reach Earth from the Sun and years to reach the outermost planets. But when we leave the solar system and consider the scale of the Milky Way, these differences shrink further into insignificance. The Milky Way itself stretches approximately 100,000 light-years across and contains between 200 and 400 billion stars, each potentially hosting planets. Our entire solar system occupies a tiny region near the edge of this massive disk, roughly 27,000 light-years from the galactic center. In terms of cosmic distances, the Earth is smaller than a grain of sand within a vast stadium that represents the Milky Way. Our planet is just a minuscule component in a galaxy teeming with stars, dust, and dark matter. When we expand our perspective to the observable universe, the scale becomes almost unimaginable. The Milky Way is only one galaxy among an estimated 2 trillion in the observable universe. The distances between galaxies are staggering, with millions of light-years separating our galactic neighborhood from even the nearest large galaxies. Entire superclusters, containing thousands of galaxies, span hundreds of millions of light-years. Voids, where very little matter exists, are tens or even hundreds of millions of light-years across. Against this colossal backdrop, Earth and humanity occupy an almost infinitesimal volume of space. The tiny scale of humans relative to the universe is amplified when considering time. Our species, Homo sapiens, has existed for roughly 300,000 years. A mere blink of an eye in the 13.8 billion-year history of the universe. The Earth itself is approximately 4.5 billion years old, still young compared to the age of the cosmos. The stars in the night sky, some of which formed billions of years before the Earth, shine across distances that take millions or billions of years for their light to reach us. In the vastness of time and space, human existence is fleeting, ephemeral, and extraordinarily localized. Even our most ambitious technological achievements pale in comparison to cosmic scales. The farthest human-made object, the Voyager 1 spacecraft, has traveled only about 23 billion kilometers from Earth as of 2025, a journey that takes decades and is still less than 1,000th of a light-year. This is still a minuscule fraction of the distance to even the nearest stars, let alone the galaxies at the edge of the observable universe. The contrast between human endeavors and cosmic distances underscores both our ingenuity and the limitations imposed by our small scale. Recognizing our tiny place in the universe also shifts our perspective on everyday concerns. The immense scale of galaxies, superclusters, and cosmic voids reminds us that Earth is a singular oasis in an otherwise vast and largely empty cosmos. It emphasizes the fragility of our environment and the uniqueness of our vantage point, orbiting a single star in a spiral galaxy among trillions of others. At the same time, it underscores the interconnectedness of everything. The elements in our bodies were forged in stars billions of years ago, and our planet is part of a larger cosmic system governed by universal laws. Philosophically, this human perspective can be both humbling and inspiring. On one hand, the universe dwarfs our achievements and concerns, placing them in the context of a vast, ancient, and ever-expanding cosmos. On the other hand, it highlights the extraordinary fact that beings so small in scale and duration are capable of understanding, measuring, and conceptualizing the universe itself. Humans have built telescopes capable of observing galaxies billions of light-years away, satellites that measure the cosmic microwave background, and mathematical models that describe the expansion of space and the distribution of dark matter and dark energy. The ability of our tiny species to comprehend the vast universe is a testament to curiosity, intelligence, and imagination. From a visual perspective, imagining the Earth as a single pixel within the Milky Way helps underscore our cosmic minuteness. Each pixel in a digital image of the galaxy could represent a star, and yet the Earth would not even register. Expand this metaphor to include the billions of galaxies across the observable universe, and the Earth becomes a nearly invisible point in a nearly infinite cosmic tapestry. Despite this tiny size, our observations and scientific inquiry allow us to map, measure, and explore structures spanning billions of light-years, revealing the universe's complexity and grandeur. Ultimately, the human perspective in relation to the universe is defined by contrast. We are incredibly small in both space and time, yet capable of extraordinary understanding. We exist on a tiny planet within a modest galaxy, itself one of trillions in the observable universe, yet we can trace the history of the cosmos back to the first light from the Big Bang, map the cosmic web, and detect the influence of dark energy on expansion. This duality, small in scale but capable of understanding enormous structures, adds to the awe and wonder inspired by the universe, highlighting both our fragility and our capacity for cosmic insight. Contemplating the sheer size of the universe inevitably leads to deep philosophical reflection, compelling us to consider not only the physical dimensions of space but also our place within it. The universe's vastness challenges the human sense of centrality and importance. It reveals that Earth is but a tiny, transient speck in a cosmos that stretches across billions of light-years and has existed for nearly 14 billion years. This realization can be both humbling and liberating, forcing us to confront the scale of reality and reconsider what it means to exist in such a grand context. The immensity of the universe invites a reconsideration of anthropocentrism, the idea that humans or Earth occupy a privileged position in the cosmos. For centuries, humans believed that Earth was the center of creation, a notion reinforced by observable celestial patterns and philosophical frameworks. Copernicus, Galileo, and subsequent astronomers challenged this view, showing that Earth orbits the Sun, which itself is merely one star among billions in the Milky Way. Extending this perspective further to the billions of galaxies in the observable universe underscores the notion that there is no center or edge, no cosmic vantage point that is inherently special. We exist on a modest planet orbiting a relatively ordinary star, in a galaxy that is one of countless others, within a universe whose true extent may be infinite. This realization prompts reflection on meaning and significance. On a purely physical scale, humans and Earth are negligible. Yet, the ability to perceive, understand, and contemplate the universe itself imbues our existence with a unique kind of significance. We are the observers of the cosmos, capable of measuring light that has traveled billions of years, mapping the cosmic web, and exploring the physical laws that govern all matter and energy. Our consciousness allows us to grasp ideas that far surpass our physical dimensions, granting a type of importance rooted not in size, but in awareness and comprehension. In this sense, the vastness of the universe does not diminish humanity. It contextualizes our role as thinkers and explorers within an immense, dynamic reality. The philosophical implications also extend to the concept of time. Cosmic timescales dwarf human history. The age of the universe is roughly 13.8 billion years, while modern humans have existed for just a few 100,000 years. In this context, individual lifetimes, civilizations, and even species seem ephemeral. Yet the universe's vast timeline offers a kind of continuity and resilience. While individual lives are brief, the cosmos endures, evolves, and contains processes that stretch across incomprehensible durations. This perspective encourages humility, fostering a sense of stewardship for our planet and an appreciation for the fleeting nature of existence. Furthermore, the vastness of the universe evokes a sense of mystery and wonder. It challenges us to confront questions that may never have definitive answers. Are we alone? Is the universe infinite? Or is it part of an even larger multiverse? What is the ultimate fate of all cosmic structures? Grappling with these questions inspires both scientific inquiry and philosophical reflection, bridging empirical investigation with the human search for meaning. The universe's enormity reveals our limitations but also highlights the capacity of human curiosity and imagination to transcend those limitations. The contemplation of cosmic scale also affects our perception of life, value, and ethics. Recognizing that Earth is a tiny oasis in a vast, mostly empty cosmos can foster a profound appreciation for the rarity and fragility of life. It encourages environmental stewardship and reinforces the interconnectedness of all life on our planet, emphasizing that while humans are small in the cosmic sense, our choices have real consequences within our immediate environment. Philosophically, understanding the universe's size can inspire a sense of shared responsibility and collective purpose, as we occupy a unique vantage point from which we can observe, study, and protect our tiny corner of the cosmos. At the same time, the universe's immensity provokes awe. Observing light from distant galaxies that left billions of years ago, mapping the cosmic microwave background, and tracing the effects of dark energy on the expansion of space all evoke a sense of wonder that transcends ordinary human experience. This awe is not simply aesthetic. It is a cognitive response to the recognition that the universe operates on scales far beyond human intuition. Such reflection can inspire creativity, philosophy, science, and art, shaping the ways humans interpret their place in the cosmos. The philosophical angle also raises questions about purpose. The universe does not have a prescribed intention, yet humans can derive meaning through exploration, understanding, and connection. Our capacity to comprehend phenomena like cosmic expansion, the cosmic web, and the age of the universe allows us to participate in a narrative far larger than ourselves. The recognition that the cosmos is vast, ancient, and possibly infinite challenges narrow, self-centered views of existence, encouraging a broader, more expansive perspective. In essence, contemplating the universe's size is a humbling and transformative exercise. It reminds us that we are physically small and temporally brief, yet capable of extraordinary insight. The cosmos invites us to reflect on significance, curiosity, and the nature of existence itself. By situating ourselves within the immensity of space and time, we gain perspective on our accomplishments, limitations, and responsibilities. The universe is a vast, awe-inspiring, and ultimately incomprehensible reality, and our awareness of it elevates our understanding of life, knowledge, and meaning. Despite the incredible progress in understanding the cosmos, some of the most fundamental questions about the universe remain unanswered, inviting both scientific investigation and philosophical contemplation. One of the biggest open questions is whether the universe is finite or infinite in extent. While we can measure the observable universe, which spans a radius of roughly 46 billion light-years, this is only the portion from which light has had time to reach us. Beyond this horizon, the universe may continue indefinitely, or it may have some boundary or curvature that we have yet to detect. Current observations suggest that the universe is spatially flat on large scales, which is consistent with an infinite universe, but this is not definitive proof. The possibility remains that the universe is finite but unbounded, curving back on itself in a way analogous to the surface of a sphere but in higher dimensions. The question of infinity is not only a matter of size but also of nature. An infinite universe would contain an unbounded number of galaxies, stars, and planets, and potentially an infinite number of variations of cosmic structures and even life forms. This leads to mind-bending philosophical implications, such as the idea that configurations of matter identical to our own might exist elsewhere, somewhere unimaginably far away. In contrast, a finite universe would have a limit in extent, even if it is far beyond the reach of current observation. A finite universe might be curved or folded in a higher dimensional space, allowing it to have no edge while still being limited in total volume. Determining which scenario is correct is one of the most profound questions in cosmology. Another open question concerns the possibility of a multiverse. Some theories of cosmology, particularly those related to inflation and quantum mechanics, suggest that our universe might be just one of countless others, each with its own physical laws, constants, and initial conditions. If the multiverse exists, the universe we observe would be merely a local patch in an unimaginably vast collection of universes, some possibly similar to ours and others wildly different. This idea challenges traditional notions of the universe as a singular, self-contained entity and raises questions about what it means to exist in a broader cosmological context. Although currently speculative, the multiverse concept provides a framework for understanding certain fine-tuned aspects of physics, such as the precise values of fundamental constants that allow for the existence of life. Even within the observable universe, there are open questions about structure, composition, and evolution. We know that dark matter and dark energy dominate the universe's energy density, yet their true nature remains mysterious. We do not fully understand how dark energy drives the accelerated expansion or whether its properties might change over time. Similarly, while dark matter is inferred from gravitational effects on visible matter and cosmic structures, we have not yet directly detected it. These unknown components shape the large-scale structure of the universe and influence its ultimate fate, meaning that our understanding of the cosmos is still incomplete despite our detailed observations. The ultimate size of the universe is also an open question. While the observable universe has a measurable boundary defined by the distance light has traveled since the Big Bang, this does not indicate an absolute edge. Space itself may continue endlessly beyond what we can see, or it may loop back on itself in ways that are difficult to detect. Our observational tools are limited by the speed of light, and even future technology will not allow us to see beyond regions from which light has not yet had time to arrive. The universe could be vastly larger than the observable portion, potentially containing structures and phenomena that are forever beyond our reach. Cosmologists also grapple with the possibility that the universe's fundamental laws might vary in different regions or in different universes if the multiverse hypothesis is correct. This raises profound questions about the universality of physics. Are the constants of nature truly universal, or are they just local properties of the patch of the cosmos we inhabit? Could life exist under entirely different physical laws elsewhere? These questions stretch the imagination and illustrate that even with all the observational data we have collected, the universe remains mysterious in ways that are fundamentally inaccessible to direct measurement. Another dimension of open questions is temporal, the origin and fate of the universe. While the Big Bang theory describes the expansion of the universe from an initially hot, dense state, questions about what preceded it remain unanswered. Did the universe emerge from a singularity? Was there a before the Big Bang, or is time itself a property that began at that moment? Similarly, the long-term fate of the universe is linked to the properties of dark energy. Will expansion continue forever, leading to a cold, empty cosmos, or could there be a reversal or phase change that triggers a different cosmic destiny? These uncertainties highlight that understanding the size of the universe is inseparable from understanding its temporal evolution. Even the simplest sounding questions about the universe's boundaries, extent, and overall structure lead to profound philosophical implications. If the universe is infinite, what does that mean for uniqueness, causality, and existence? If there is a multiverse, what does it imply about the limits of human knowledge and observation? The recognition that there are aspects of reality potentially forever beyond our perception both humbles and inspires. It challenges us to develop new theories, new observational techniques, and new ways of conceptualizing space and time. In essence, the universe presents open questions that reach far beyond simple measurement. We do not yet know if it is finite or infinite, bounded or unbounded, singular or part of a multiverse. Even within the observable universe, the nature of its dark components, the exact distribution of matter, and the ultimate trajectory of expansion remain mysteries. These unanswered questions are not shortcomings but invitations, opportunities for science, philosophy, and human curiosity to explore realms that extend far beyond what we can currently perceive. The universe's size and complexity remind us that while we can measure, observe, and theorize, some truths may remain forever elusive, pushing the boundaries of understanding and imagination. As we draw our contemplation of the universe to a close, it is impossible not to be overwhelmed by the sheer scale, complexity, and beauty of the cosmos. From the tiny confines of Earth to the vast expanses of billions of galaxies stretching across billions of light-years, the universe defies human comprehension at every turn. Every discovery we make opens up new mysteries, revealing layers of reality that are simultaneously familiar in principle and astonishingly alien in scale. Even as we map the cosmic web, measure the cosmic microwave background, and detect the subtle influences of dark energy, the universe retains an awe-inspiring sense of mystery, a vast, ever-expanding enigma that challenges both the imagination and our scientific understanding. The true size of the universe may forever elude our grasp. The observable universe, with a radius of about 46 billion light-years, is only the portion accessible to our instruments and limited by the speed of light. Beyond this horizon may lie an expanse far larger, possibly infinite, filled with galaxies, matter, and phenomena that we may never detect. The universe may contain structures and laws of physics that differ from what we know, or it may be part of an even grander multiverse, where our local cosmos is but a tiny patch in an incomprehensible mosaic of realities. Even the idea that we may never fully measure its totality does not diminish its wonder, it amplifies it. Science itself is driven by this very sense of awe and curiosity. The mysteries of the universe, the unknown nature of dark matter, the enigma of dark energy, the origins of the cosmos, and the possibility of regions forever beyond observation, serve as catalysts for exploration and discovery. Each question propels humanity to invent new instruments, develop new theories, and push the boundaries of understanding. The universe is simultaneously a laboratory, a canvas, and a challenge, inviting generations of scientists, thinkers, and dreamers to explore its depths, to question the known, and to expand the horizons of human knowledge. Yet beyond the realm of measurement and calculation, the universe inspires a profound emotional response. Contemplating its vastness, the light that has traveled billions of years, and the intricate cosmic web that spans unimaginable distances evokes a sense of humility and wonder. We are reminded of the fragility of life, the fleeting nature of existence, and the extraordinary conditions that allow consciousness to emerge on a tiny planet orbiting an ordinary star. The universe is enormous, ancient, and magnificent, yet it is also the arena in which our minds can reach toward understanding, in which curiosity finds expression, and in which imagination can roam freely across time and space. This is not merely poetic, it has practical consequences. It drives scientific inquiry, fuels technological innovation, and motivates exploration. The desire to understand the universe leads to telescopes peering into the farthest reaches of space, satellites measuring the faintest cosmic signals, and simulations recreating billions of years of cosmic evolution. Every advance brings us closer to understanding our place in the cosmos, yet each new discovery also reminds us how much remains unknown. The vastness of the universe is a perpetual invitation to learn, to wonder, and to expand the frontiers of knowledge. Even in recognizing our smallness, there is empowerment. While Earth and humanity occupy only an infinitesimal fraction of the cosmic stage, our capacity to observe, reason, and theorize allows us to engage meaningfully with the universe. We can comprehend structures that span billions of light-years, trace the evolution of galaxies across cosmic time, and detect the faint whispers of phenomena that occurred nearly 14 billion years ago. This is remarkable, given the minuscule scale of our physical existence, and it underscores the unique power of human cognition and curiosity. The universe, in all its incomprehensible magnitude, also teaches patience and perspective. Its processes unfold over billions of years, far exceeding the span of any single human life. Stars are born and die, galaxies merge and evolve, and cosmic expansion continues at a gradual pace that only reveals its effects over eons. Observing these processes requires not only sophisticated instruments but also the ability to think in terms far beyond ordinary experience. The vastness of time and space challenges our perception and forces us to expand our sense of scale, blending science with philosophy, observation with imagination, and curiosity with humility. In the end, what makes the universe truly awe-inspiring is not just its size, nor merely its complexity, but the endless frontier of mystery that it presents. It is a realm where every answer sparks new questions, where the known and unknown are perpetually intertwined, and where human inquiry, creativity, and wonder are continuously tested and expanded. Whether the universe is finite or infinite, whether it is alone or part of a larger multiverse, we can be certain of one thing: it is far beyond complete comprehension, and this very mystery is what propels science forward, ignites imagination, and inspires humanity to reach ever farther. As we gaze at the night sky, measure the faint glow of the cosmic microwave background, and explore distant galaxies billions of light-years away, we are reminded that the universe is both a home and a frontier. Its vastness dwarfs us physically, but it elevates us intellectually. Its mysteries humble us, but they also drive our search for understanding. In contemplating the immensity of space, the age of the cosmos, and the limits of observation, we are faced with the sublime truth. The universe is beyond comprehension, and it is precisely this boundless enigma that continues to inspire, challenge, and move science and humanity forward. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.